Warning: empty page. Digital Logic and Computer Design M. Morris Mano, Professor of Engineering, California State University, Los Angeles. Copyright 2016 Pearson India Education Services Private Ltd. Published by Pearson India Education Services Private Ltd, CIN, U72200TN 2005 PTC 057128, formerly known as TutorVista Global Private Ltd, licensee of Pearson Education in South Asia. No part of this ebook may be used or reproduced in any manner whatsoever without the publisher's prior written consent. This ebook may or may not include all assets that were part of the print version. The publisher reserves the right to remove any material in this ebook at any time. ISBN 978-93-325-8604-8, ISBN 978-93-325-4252-5. Head Office: A8A, 7th floor, Knowledge Boulevard, Sector 62, Noida 201309, Uttar Pradesh, India. Registered Office: 4th floor, Software Block, Elnett Software City, TS 140, Block 2 and 9, Rajiv Gandhi Salai, Tarmani, Chennai 60113, Tamil Nadu, India. www.pearson.co.in. Email: Company Secretary, India@pearson.com. Fax: 080-30461003. Phone: 080-30461060. Contents: Preface 9.1 Binary Systems 1.1.1 Digital Computers and Digital Systems 1.1.2 Binary Numbers 3.1.3 Number-Based Conversions 6.1.4 Octal and Hexadecimal Numbers 8.1.5 Complements 9. 1.6 Binary Codes 14 1.7 Binary Storage and Registers 21.8 Binary Logic 23 1.9 Integrated Circuits 26 2 Boolean Algebra and Logic Gates 31 2.1 Basic Definitions 31 2.2 Axiomatic Definition of Boolean Algebra 32 2.3 Basic Theorems and Properties of Boolean Algebra 35 2.4 Boolean Functions 39 2.5 Canonical and Standard Forms 43 2.6 Other Logic Operations 49 2.7 Digital Logic Gates 51 2.8 IC Digital Logic Families 54 3 Simplification of Boolean Functions 65 3.1 The Map Method 65 3.22 and 3 Variable Maps 65. 4 Contents 3.3 4 Variable Maps 69 3.45 and 6 Variable Maps 72 3.5 Product of Sum Simplification 75 3.6 NAND and NOR Implementation 77 3.7 Other two-level implementations 83 3.8 Don't Care Conditions 87 3.9 The Tabulation Method 89 3.10 Determination of Prime Implicants 93.11 Selection of Prime Implicants 94 3.12 Concluding Remarks 96 4 Combinational Logic 103 4.1 Introduction 103 4.2 Design Procedure 104 4.3 Adders 105 4.4 Subtractors 109 4.5 Code Conversion 111 4.6 Analysis Procedure 113 4.7 Multilevel NAND Circuits 117 4.8 Multilevel NOR Circuits 124 4.9 Exclusive OR and Equivalence Functions 127 5 Combinational Logic with MSI and LSI 137 5.1 Introduction 137 5.2 Binary Parallel Adder 138 5.3 Decimal Adder 143 5.4 Magnitude Comparator 145 5.5 Decoders 147 5.6 Multiplexers 156 5.7 Read-Only Memory ROM 161 5.8 Programmable Logic Array PLA 167 5.9 Concluding Remarks 173 6 Sequential Logic 179 6.1 Introduction 179 6.2 Flip-flops 180 Contents version 6.3 Triggering of flip-flops 185 6.4 Analysis of clocked sequential circuits 193 6.5 State reduction and assignment 198 6.6 Flip-flop excitation tables 204 6.7 Design procedure 206 6.8 Design of counters 215 6.9 Design with state equations 218 7 Registers, counters, and the memory unit 229 7.1 Introduction 229 7.2 Registers 237.3 Shift registers 235 7.4 Ripple counters 242 7.5 Synchronous counters 247 7.6 Timing sequences 253 7.7 The memory unit 258 7.8 Examples of random access memories 262 8 Register transfer logic 271 8.1 Introduction 271 8.3 Arithmetic, logic, and shift microoperations 281 8.4 Conditional control statements 284 8.5 Fixed point binary data 285 8.6 Overflow 289 8.7 Arithmetic shifts 291 8.8 Decimal data 293 8.9 Floating point data 294 8.10 Non-numeric data 297 8.11 Instruction codes 308.12 Design of a simple computer 3049 Processor logic design 317.9.1 Introduction 317.9.2 Processor organization 318 9.3 Arithmetic logic unit 325 9.4 Design of arithmetic circuit 326 9.5 Design of logic circuit 331 6 Contents 9.6 Design of arithmetic logic unit 335 9.7 Status register 338 9.8 Design of shifter 340 9.9 Processor unit 342 9.10 Design of accumulator 346 10 Control logic design 362 10.1 Introduction 362 10.2 Control organization 364 10.3 Hardwired control Example 1 369 10.4 Microprogram control 376 10.5 Control of processor unit 382 10.6 Hardwired control Example 2 386 10.7 PLA Control 393 10.8 Microprogram Sequencer 396 11 Computer Design 407 11.1 Introduction 407 11.2 System Configuration 408 11.3 Computer Instructions 411 11.4 Timing and Control 417 11.5 Execution of Instructions 419 11.6 Design of Computer Registers 424 11.7 Design of Control 429 11.8 Computer Console 438 12 Microcomputer System Design 443 12.1 Introduction 443 12.2 Microcomputer Organization 445 12.3 Microprocessor Organization 449 12.4 Instructions and Addressing Modes 456 12.5 Stack, Subroutines, and Interrupt 463 12.6 Memory Organization 471 12.7 Input-Output Interface 474 12.8 Direct Memory Access 484 Contents 713 Digital Integrated Circuits 492 13.1 Introduction 492 13.2 Bipolar Transistor Characteristics 494 13.3 RTL and DTL Circuits 497 13.4 Integrated Injection Logic I2L 500 13.5 Transistor Logic TTL 502 13.6 Emitter Coupled Logic ECL 511 13.7 Metal Oxide Semiconductor MOS 513 13.8 Complementary MLES CMOS 515 Appendix 521 Index 537 This page is intentionally left blank. Preface. Digital logic is concerned with the interconnection among digital components and modules and is a term used to denote the design and analysis of digital systems. The best-known example of a digital system is the general-purpose digital computer. This book presents the basic concepts used in the design and analysis of digital systems and introduces the principles of digital computer organization and design. It provides various methods and techniques suitable for a variety of digital system design applications. It covers all aspects of digital systems from the electronic gate circuits to the complex structure of microcomputer systems. Chapters 1 through 6 present digital logic design techniques from the classical point of view. Boolean algebra and truth tables are used for the analysis and design of combinational circuits and state transition techniques for the analysis and design of sequential circuits. Chapters 7 through 12 present digital system design methods from the register transfer point of view. The digital system is decomposed into register subunits, and the system is specified with a list of register transfer statements that describe the operational transfers among the information stored in registers. The register transfer method is used for the analysis and design of processor units, control units, a computer central processor, and for describing the internal operations of microprocessors and microcomputers. Chapter 13 deals with the electronics of digital circuits and presents the most common integrated circuit digital logic families. The components used to construct digital systems are manufactured in integrated circuit form. Integrated circuits contain a large amount of interconnected digital circuits within a single small package. Medium-scale integration, MSI, devices provide digital functions, and large-scale integration, LSI, devices provide complete computer modules. It is very important for the logic designer to be familiar with the various digital components encountered in integrated circuit form. For this reason, many MSI and LSI circuits are introduced throughout the book and their logical function fully explained. The use of integrated circuits in the design of digital systems is illustrated by means of examples in the text and in problems at the end of the chapters. This book was originally planned as a second edition to the author's Computer Logic Design, Prentice Hall, 1972. Because of the amount of new material added and the extensive revisions that have taken place, it seems more appropriate to adopt a new title for the present text. About 1/3 of the text is material that appears in the previous book. The other 2/3 constitutes new or revised information. The underlying factors for the revisions and additions arise from developments in the digital electronics technology. Great emphasis is given to MSI and LSI circuits and to design methods using integrated circuits. The book covers various LSI. Preface. Components of the bit slice and microcomputer variety. It presents applications of the read-only memory, ROM, and programmable logic array, PLA. Moreover, further developments in the register transfer method of design mandated a complete rewriting of the second half of the book. Chapter 1 presents various binary systems suitable for representing information in digital components. The binary number system is explained and binary codes are illustrated to show the representation of decimal and alphanumeric information. Binary logic is introduced from an intuitive point of view before proceeding with a formal definition of Boolean algebra. The basic postulates and theorems of Boolean algebra are found in Chapter 2. The correlation between a Boolean expression and its equivalent interwhat connection of gates is emphasized. All possible logic operations for two variables are investigated, and from that, the most useful logic gates are derived. The characteristics of digital gates available in integrated circuit form are presented early in this chapter, but a more detailed analysis describing the internal construction of the gates is left for the last chapter. Chapter 3 supplies the map and tabulation methods for simplifying Boolean functions. The map method is used to simplify digital circuits constructed with AND, OR, NAND, NOR, and wired logic gates. The various simplification procedures are summarized in tabular form for easy reference. Design and analysis procedures for combinational circuits are provided in Chapter 4. Some basic components used in the design of digital systems, such as adders and code converters, are introduced as design or analysis examples. The chapter investigates possible implementations using multilevel NAND and NOR combinational circuits. Chapter 5 deals with combinational logic MSI and LSI components. Often used functions such as parallel adders, decoders, and multiplexers are explained, and their use in the design of combinational circuits is illustrated with examples. The read-only memory, ROM, and programmable logic array, PLA, are introduced, and their usefulness in the design of complex combinational circuits is demonstrated. Chapter 6 outlines various methods for the design and analysis of clocked sequential circuits. The chapter starts by presenting various types of flip-flops and the way they are triggered. The state diagram, state table, and state equations are shown to be convenient tools for analyzing sequential circuits. The design methods presented transform the sequential circuit to a set of Boolean functions that specify the input logic to the circuit flip-flops. The input Boolean functions are derived from the excitation table and are simplified by means of maps. In Chapter 7, a variety of registers, shift registers, and counters similar to those available in integrated circuit packages is presented. The operation of the random access memory, RAM, is also explained. The digital functions introduced in this chapter are the basic building blocks from which more complex digital systems are constructed. Chapter 8 introduces the register transfer method for describing digital systems. It shows how to express in symbolic form the operation sequence among the registers of a digital system. Symbols are defined for interregister transfer, arithmetic, logic, and shift microoperations. The different data types that are stored in computer registers are covered in detail. Some typical examples are used to show how computer instructions are represented in binary coded form and how the operations specified by instructions can be expressed with register transfer. Statements. The chapter concludes with the design of a very simple computer to demonstrate their register transfer method of digital system design. Chapter 9 is concerned with the processor unit of digital computers. It discusses alternatives for organizing a processor unit with buses or scratchpad memory, a typical arithmetic logic. Preface 11. Unit ALU is presented and a procedure is developed for the design of any other ALU configuration. Other components commonly found in processors, such as shifters and status registers, are also presented. The design of a general-purpose accumulator register is undertaken, starting from a specified set of register transfer operations and culminating in a logic diagram. 4 methods of control logic design are introduced in Chapter 10. 2 of the methods constitute hardwired control. The other 2 introduce the concept of microprogramming and how to design a controller with the programmable logic array, PLA. The 4 methods are redemonstrated by means of examples that show the development of design algorithms and the procedure for obtaining the control circuits for the system. The last section introduces an LSI microprogram sequencer and shows how it can be used to design a microprogram control unit. Chapter 11 is devoted to the design of a small digital computer. The registers in the computer are defined and a set of computer instructions is specified. The computer description is formalized with register transfer statements that specify the microoperations among the registers as well as the control functions that initiate these microoperations. It is then shown that the set of microoperations can be used to design the data processor part of the computer. The control functions in the list of register transfer statements supply the information for the design of the control unit. The control unit for the computer is designed by 3 different methods: hardwired control, PLA control, and microprogram control. Chapter 12 focuses on various LSI components that form a microcomputer system. The organization of a typical microprocessor is described and its internal operation explained. A typical set of instructions for the microprocessor is presented and various addressing modes are explained. The operation of a stack and the handling of subroutines and interrupts is covered from the hardware point of view. The chapter also illustrates the connection of memory chips to a microprocessor bus system and the operation of various interface units that communicate with input-output devices. It concludes with a description of the direct memory access mode of transfer. Chapter 13 details the electronic circuits of the basic gate in 7 integrated circuit logic families. This final chapter should be considered as an appendix and can be omitted if desired. Chapter 13 assumes prior knowledge of basic electronics, but there is no specific prerequisite for the rest of the book. Every chapter includes a set of problems and a list of references. Answers to selected problems appear and the appendix to provide an aid for the student and to help the independent reader. The book is suitable for a course in digital logic and computer design in an electrical or computer engineering department. It can also be used in a computer science department for a course in computer organization. Parts of the book can be used in a variety of ways. 1. As a first course in digital logic or switching circuits by covering chapters 1 through 7 and possibly chapter 13. 2. As a second course in digital computer logic with a prerequisite of a course in basic switching circuits by covering chapter 5 and chapters 7 through 12. 3. As an introduction to the hardware of microprocessors and microcomputers by covering chapters 8 through 12. In conclusion, I would like to explain the philosophy underlying the material presented in this book. The classical method has been predominant in the past for describing the operations of digital circuits. With the advent of integrated circuits, and especially the introduction of microcomputer LSI components, the classical method seems to be far removed from practical applications, although the classical method for describing complex digital systems is not directly applicable. The basic concepts of Boolean algebra, combinational logic, and sequential logic procedures are still important for understanding the internal construction of many digital functions. 12. Preface. On the other hand, the register transfer method provides a better representation for describing the operations among the various modules in digital systems. It is concerned with the transfer of bit strings in parallel and may be considered to be one level higher in the hierarchy of digital system representation. The transition from the classical to the register transfer method is made in the book by way of integrated circuit MSI functions. Chapters 5 and 7 cover many digital functions which are available in integrated circuits. Their operation is explained in terms of gates and flip-flops that make up the particular digital circuit. Each MSI circuit is considered as a functional unit that performs a particular operation. This operation is then described in the register transfer method of notation. Thus, the analysis and design of registers and other digital functions is done by means of the classical method, but the use of these functions in describing the operations of a digital system is specified by means of register transfer statements. The register transfer method is then used to define computer instructions, to express digital operations in concise form, to demonstrate the organization of digital computers, and to specify the hardware components for the design of digital systems. I wish to express my thanks to Dr. John L. Fike for reviewing the original manuscript and to Professor Victor Pays for pointing out corrections while teaching a course using the manuscript. Most of the typing was done by Mrs. Lucy Albert, and her skilled help is gratefully appreciated. My greatest thanks go to my wife for all the suggestions she made for improving the readability of the text and for her encouragement and support during the preparation of this book. M. Morris Mano. Publishers' Acknowledgement. The publishers would like to thank Shivani Goel, Thopper University, Kolkata, for his valuable suggestions and inputs for enhancing the content of this book to suit the requirement of Indian universities. 1.1 Digital Computers and Digital Systems. Digital computers have made possible many scientific, industrial, and commercial advances that would have been unattainable otherwise. Our space program would have been impossible without real-time, continuous computer monitoring, and many business enterprises function efficiently only with the aid of automatic data processing. Computers are used in scientific calculations, commercial and business data processing, air traffic control, space guidance, the educational field, and many other areas. The most striking property of a digital computer is its generality. It can follow a sequence of instructions, called a program, that operates on given data. The user can specify and change programs and/or data according to the specific need. As a result of this flexibility, general-purpose digital computers can perform a wide variety of information processing tasks. The general-purpose digital computer is the best-known example of a digital system. Other examples include telephone switching exchanges, digital voltmeters, frequency counters, calculating machines, and teletype machines. Characteristic of a digital system is its manipulation of discrete elements of information. Such discrete elements may be electric impulses, the decimal digits, the letters of an alphabet, arithmetic operations, punctuation marks, or any other set of meaningful symbols. The juxtaposition of discrete elements of information represents a quantity of information. For example, the letters D, O, and G form the word dog. The digits 237 form a number. Thus, a sequence of discrete elements forms a language, that is, a discipline that conveys information. Early digital computers were used mostly for numerical computations. In this case, the discrete elements used are the digits. From this application, the term digital computer has emerged. A more appropriate name for a digital computer would be a discrete information processing system. Discrete elements of information are represented in a digital system by physical quantities called signals. Electrical signals such as voltages and currents are the most common. The signals in all present-day electronic digital systems have only two discrete values and are said to be binary. The digital system designer is restricted to the use of binary signals because of the lower reliability of many-valued electronic circuits. In other words, a circuit with 10 states, using one discrete voltage value for each state, can be designed, but it would possess a very low reliability of operation. In contrast, a transistor circuit that is either on or off has two possible signal values and can be constructed to be extremely reliable. Because of this physical restriction of components, and because human logic tends to be binary, digital systems that are constrained to take discrete values are further constrained to take binary values. Discrete quantities of information emerge either from the nature of the process or may be purposely quantized from a continuous process. For example, a payroll schedule is an inherently 2 Chapter 1 discrete process that contains employee names, social security numbers, weekly salaries, income taxes, etc. An employee's paycheck is processed using discrete data values such as letters of the alphabet, names, digits, salary, and special symbols such as $. On the other hand, a research scientist may observe a continuous process but record only specific quantities in tabular form. The scientist is thus quantizing his continuous data. Each number in his table is a discrete element of information. Many physical systems can be described mathematically by differential equations whose solutions as a function of time give the complete mathematical behavior of the process. An analog computer performs a direct simulation of a physical system. Each section of the computer is the analog of some particular portion of the process under study. The variables in the analog computer are represented by continuous signals, usually electric voltages that vary with time. The signal variables are considered analogous to those of the process and behave in the same manner. Thus, measurements of the analog voltage can be substituted for variables of the process. The term analog signal is sometimes substituted for continuous signal because analog computer has come to mean a computer that manipulates continuous variables. To simulate a physical process in a digital computer, the quantities must be quantized. When the variables of the process are presented by real-time continuous signals, the latter are quantized.
When the variables of the process are presented by real-time continuous
When the variables of the process are presented by real-time continuous signals, the latter are quantized by an analog-to-digital conversion device. A physical system whose behavior is described by mathematical equations is simulated in a digital computer by means of numerical methods. When the problem to be processed is inherently discrete, as in commercial applications, the digital computer manipulates the variables in their natural form. A block diagram of the digital computer is shown in Figure 1.1. The memory unit stores programs as well as input, output, and intermediate data. The processor unit performs arithmetic and other data processing tasks as specified by a program. The control unit supervises the flow of information between the various units. The control unit retrieves the instructions one by one from the program which is stored in memory. For each instruction, the control unit informs the processor to execute the operation specified by the instruction. Both program and data are stored in memory. The control unit supervises the program instructions, and the processor manipulates the data as specified by the program. Control unit processor or arithmetic unit storage or memory unit. Input devices and control output devices and control figure 1.1 block diagram of a digital computer. Binary System 3. The program and data prepared by the user are transferred into the memory unit by means of an input device, such as punch card reader or a teletypewriter. An output device, such as a printer, receives the result of the computations, and the printed results are presented to the user. The input and output devices are special digital systems driven by electromechanical parts and controlled by electronic digital circuits. An electronic calculator is a digital system similar to a digital computer, with the input device being a keyboard and the output device a numerical display. Instructions are entered in the calculator by means of the function keys, such as plus and minus. Data are entered through the numeric keys. Results are displayed directly in numeric form. Some calculators come close to resembling a digital computer by having printing capabilities and programmable facilities. A digital computer, however, is a more powerful device than a calculator. A digital computer can accommodate many other input and output devices. It can perform not only arithmetic computations but logical operations as well, and can be programmed to make decisions based on internal and external conditions. A digital computer is an interconnection of digital modules. To understand the operation of each digital module, it is necessary to have a basic knowledge of digital systems and their general behavior. The first half of this book deals with digital systems in general to provide the background necessary for their design. The second half of the book discusses the various modules of the digital computer, their operation and design. The operational characteristics of the memory unit are explained in Chapter 7. The organization and design of the processor unit is undertaken in Chapter 9. Various methods for designing the control unit are introduced in Chapter 10. The organization and design of a small, complete digital computer is presented in Chapter 11. A processor, when combined with a control unit, forms a component referred to as a central processor unit or CPU. A CPU enclosed in small integrated circuit package is called a microprocessor. The memory unit, as well as the part that controls the interface between the microprocessor and the input and output devices, may be enclosed within the microprocessor package or may be available in other small integrated circuit packages. A CPU combined with memory and interface control to form a small-sized computer is called a microcomputer. The availability of microcomputer components has revolutionized the digital system design technology, giving the designer the freedom to create structures that were previously uneconomical. The various components of a microcomputer system are presented in Chapter 12. It has already been mentioned that a digital computer manipulates discrete elements of information and that these elements are represented in the binary form. Operands used for calculations may be expressed in the binary number system. Other discrete elements, including the decimal digits, are represented in binary codes. Data processing is carried out by means of binary logic elements using binary signals. Quantities are stored in binary storage elements. The purpose of this chapter is to introduce the various binary concepts as a frame of reference for further detailed study in the succinct chapters. 1.2 Binary numbers. A decimal number such as 7392 represents a quantity equal to 7 thousands plus 3 hundreds plus 9 tens plus 2 units. The thousands, hundreds, etc. are powers of 10 implied by the position of the coefficients. To be more exact, 7392 should be written as 7 by 103 plus 3 by 102 plus 9 by 101 plus 2 by 100. For Chapter 1. However, the convention is to write only the coefficients and from their position deduce the necessary powers of 10. In general, a number with a decimal point is represented by a series of coefficients as follows: A5, A4, A3, A2, A1, A0, A1, A2, A3. The AJ coefficients are one of the 10 digits 0, 1, 2, 9, and the subscript value j gives the place value and, hence, the power of 10 by which the coefficient must be multiplied. Plus 105 A5 104 A4 103 A3 10 to 100 A0 A 110 to 2A 210 to 3A3. The decimal number system is said to be of base, or radix, 10 because it uses 10 digits and the coefficients are multiplied by powers of 10. The binary system is a different number system. The coefficients of the binary number system have two possible values, 0 and 1. Each coefficient aj is multiplied by 2j. For example, the decimal equivalent of the binary number 11,010.11 is 26.75, as shown from the multiplication of the coefficients by powers of 2. 1 times 24 plus 1 times 23 plus 0 times 22 plus 1 times 21 plus 0 times 20 plus 1 times 2 minus 1 plus 1 times 2 minus 2 is equal to 26.75. In general, a number expressed in base R system has coefficients multiplied by powers of R. Rn plus A2 plus A1, R plus A0 dot Rn1n, R2n 1 plus R1, R2 dot Rm A1 A2 Am. The coefficients aj range in value from 0 to R1. To distinguish between numbers of different bases, we enclose the coefficients in parentheses and write a subscript equal to the base used, except sometimes for decimal numbers, where the content makes it obvious that it is decimal. An example of a base 5 number is 4021.2. 5 is equal to 4 times 53 plus 0 times 52 plus 2 by 51 plus 1 by 50 plus 2 times 5L equals 511.4. 10. Note that coefficient values for base 5 can be only 0, 1, 2, 3, and 4. It is customary to borrow the needed R digits for the coefficients from the decimal system when the base of the number is less than 10. The letters of the alphabet are used to supplement the 10 decimal digits when the base of the number is greater than 10. For example, in the hexadecimal, base 16 number system, the first 10 digits are borrowed from the decimal system. The letters A, B, C, D, E, and F are used for digits 10, 11, 12, 13, 14, and 15, respectively. An example of a hexadecimal number is B65F. I6 is equal to 11 times 163 plus 6 by 162 plus 5 by 16 plus 15 equals 46687, L0. The first 16 numbers in the decimal, binary, octal, and hexadecimal systems are listed in Table 1.1. Arithmetic operations with numbers in base R follow the same rules as for decimal numbers. When other than the familiar base 10 is used, one must be careful to use only the R allowable digits. Examples of addition, subtraction, and multiplication of two binary numbers are shown below. Binary System 5 Table 1. 1 numbers with different bases: decimal, binary, octal, hexadecimal, base 10, base 2, base 8. Base 16 0 0 0 0 0 0 0 0 0 0 1 0 0 0 1 0 1 1 0 2 0 0 1 0 0 2 2 0 3 0 0 1 1 0 3 3 0 4 0 100 0 4 4 0 5 0 1 0 1 0 5 5 0 6 0 1 1 0 0 6 6 0 7 0 1 1 1 0 7 7 0 8 1000 10 8 0 9 1000 1 11 9 10 1000 10 12 A 11 1000 11 13 B 12 1100 14 C 13 11 01 15 D 14 11 10 16 E 15 11 11 17 F 1001 Quotient dividend. Divisor 1100 1 100 1 1 0 1 1 1 1 1 1 1 1100. Reminder oddend, addend, sum, 101,101 plus 100,111, 101, 0100 minuend, subtrahend, difference, 101,101 minus 100,111,000,110 multiplicand, multiplier, product, 1011 by 1011011, 0000. 101111011. The sum of two binary numbers is calculated by the same rules as in decimal, except that the digits of the sum in any significant position can be only 0 or 1. Any carry obtained in a given significant position is used by the pair of digits one significant position higher. The subtraction is slightly more complicated. The rules are still the same as in decimal, except that the borrow in a given significant position adds 2 to a minuend digit. A borrow in the decimal 11. 6 Chapter 1 system adds 10 to a minuend digit. Multiplication is very simple. The multiplier digits are always 1 or 0. Therefore, the partial products are equal either to the multiplicand or to 0. 1.3 number base conversions. A binary number can be converted to decimal by forming the sum of the powers of two of those coefficients whose value is 1. For example, 10 L 0.0 LL 2 equals 23 plus 21 plus 2 to 2 plus 2 to 3 equals 10.375, 10. The binary number has 4 L's, and the decimal equivalent is found from the sum of 4 powers of 2. Similarly, a number expressed in base R can be converted to its decimal equivalent by multiplying each coefficient with the corresponding power of R and adding. The following is an example of octal to decimal conversion. 630.4. 8 is equal to 6 times 82 plus 3 by 8 plus 4 times 8 to 1 equals 408.5, 10. The conversion from decimal to binary or to any other base R system is more convenient if the number is separated into an integer part and a fraction part, and the conversion of each part done separately. The conversion of an integer from decimal to binary is best explained by example. Example 1 to 1. Convert decimal 41 to binary. First, 41 is divided by 2 to give an integer. Quotient of 20 and a remainder of 1 to the quotient is again divided by 2 to give a new quotient and remainder. This process is continued until the integer quotient becomes 0. The coefficients of the desired binary number are obtained from the remainders as follows. Integer quotient remainder coefficient 1 is equal to 41a0 equals 1 plus 22 2 is equal to 20a1 equals 0 10 plus 0 2 is equal to 10 5a2 equals 0 plus 0 2 is equal to 5 1. 2 2a3 equals 1 plus 2 is equal to 2 1 2a4 equals 0 plus 0 is equal to 1 1 0 2a5 equals 1 plus 2 answer. 41 L0 equals A5, A4, A3, A2, A1, A0, 2 equals 101,001, 2. Binary system 7. The arithmetic process can be manipulated more conveniently as follows. Integer remainder 41, 21, 10, 0, 5, 0, 2, 1, 1, 0, 0, 1 is equal to 101,001 answer. The conversion from decimal integers to any base R system is similar to the above example, except that division is done by R instead of 2. Example 1 to 2. Convert decimal 153 to octal. The required base R is 8. First, 153 is divided by 8 to give an integer quotient of 19 and a remainder of 1. Then 19 is divided by 8 to give an integer quotient of 2 and a remainder of 3. Finally, 2 is divided by 8 to give a quotient of 0 and a remainder of 2. This process can be conveniently manipulated as follows. 153 19 1 2 3 0 2 equals 231, 8. The conversion of a decimal fraction to binary is accomplished by a method similar to that used for integers. However, multiplication is used instead of division, and integers are accumulated instead of remainders. Again, the method is best explained by example. Example 1 to 3. Convert 0.6875 L0 to binary. First, 0.6875 is multiplied by 2 to give an integer and a fraction. The new fraction is multiplied by 2 to give a new integer and a new fraction. This process is continued until the fraction becomes 0 or until the number of digits have sufficient accuracy. The coefficients of the binary number are obtained from the integers as follows. Integer fraction coefficient times 2 equals 1 0.6875 1 plus 0.3750 a 1 times 2 equals 0 0.3750 0 plus 0.7500 a 2 times 2 equals 1 0.7500 1 plus 0.5000 a 3 times 2 equals 1 0.5000 1 plus 0.0000 a 4 equals answer 0.6875 L0 0 A1 A2 A3 A4 2 0.10112 8 Chapter 1. To convert a decimal fraction to a number expressed in base r, a similar procedure is used. Multiplication is by r instead of 2, and the coefficients found from the integers may range in value from 0 to r, 1 instead of 0 and 1. Example 1 to 4. Convert 0.513, 10 to octal. 0.513 times 8 is equal to 4.1040. 0.104 times 8 is equal to 0.832. 0.832 times 8 is equal to 6.656. 0.656 times 8 is equal to 5,248. 0.248 times 8 is equal to 1.98. 0.984 times 8 is equal to 7.872. The answer, to 7 significant figures, is obtained from the integer part of the products, equals 8, 0.513, 10, 0.406517. The conversion of decimal numbers with both integer and fraction parts is done by converting the integer and fraction separately and then combining the two answers together. Using the results of examples 1 to 1 and 1 to 3, we obtain 41.6875, 10, 101, 001, 1011. 2 from examples 1 to 2 and 1 to 4, we have 153.513, L0 equals 231.406517, 8 1.4 octal and hexadecimal numbers. The conversion from and to binary, octal, and hexadecimal plays an important part in digital computers. Since 23 is equal to 8 and 24 is equal to 16, each octal digit corresponds to 3 binary digits and each hexadecimal digit corresponds to 4 binary digits. The conversion from binary to octal is easily accomplished by partitioning the binary number into groups of 3 digits each. Starting from the binary point and proceeding to the left and to the right, the corresponding octal digit is then assigned to each group. The following example illustrates the procedure.
826153001011011011110 26,153,740,610,111,100 equals 2. Conversion from binary to hex.
Conversion from binary to hexadecimal is similar, except that the binary number is divided into groups of 4 digits. 16 2C 6BF 2 10 1100 0110 1011 11110010 2C 6B F2 equals 2. The corresponding hexadecimal or octal digit for each group of binary digits is easily remembered after studying the values listed in Table 1-1. Binary System 9. Conversion from octal or hexadecimal to binary is done by a procedure reverse to the above. Each octal digit is converted to its 3-digit binary equivalent. Similarly, each hexadecimal digit is converted to its 4-digit binary equivalent. This is illustrated in the following examples. 等于67312411011101010101010
equals 6731242 equals 6 equals equals. Conversion from octal or hexadecimal to binary is done by a procedure reverse to the above.
Conversion from octal or hexadecimal to binary is done by a procedure reverse to the above. Each octal digit is converted to its 3-digit binary equivalent. Similarly, each hexadecimal digit is converted to its 4-digit binary equivalent. This is illustrated in the following examples. 等于67312411110
equals 6731242 equals 6 binary system 9. Conversion from octal equals 67312 equals 6731242 110 111 011 0010 10 100 673.124 8 360 L6 equals 306D 2001100001101. Binary numbers are difficult to work with because they require 3 or 4 times as many digits as their decimal equivalent. For example, the binary number 11111111111 is equivalent to decimal 4095. However, digital computers use
binary numbers, and it is sometimes necessary for the human operator or user to communicate directly with the machine by means of binary numbers. One scheme that retains the binary system in the computer but reduces the number of digits the human must consider utilizes the relationship between the binary number system and the octal or hexadecimal system. By this method, the human thinks in terms of octal or hexadecimal numbers and performs the required conversion by inspection when direct communication with the machine is necessary. Thus, the binary number 11111111 has 12 digits and is expressed in octal as 7,777, 4 digits, or in hexadecimal as FFF, 3 digits. During communication between people about binary numbers in the computer, the octal or hexadecimal representation is more desirable because it can be expressed more compactly with a third or a quarter of the number of digits required for the equivalent binary number. When the human communicates with the machine, through console switches or indicator lights or by means of programs written in machine language, the conversion from octal or hexadecimal to binary and vice versa is done by inspection by the human user. 1.5 Complements. Complements are used in digital computers for simplifying the subtraction operation and for logical manipulations. There are 2 types of complements for each base R system. 1. The R's complement and 2. The R1's complement. When the value of the base is substituted, the 2 types receive the names 2's and L's complement for binary numbers or 10's and 9's complement for decimal numbers. 1.5.1 The R's complement. Given a positive number n in base R with an integer part of n digits, the R's complement of n is defined as Rn. N for n is not equal to 0 and 0 for n equals 0. The following numerical example will help clarify the definition. Equals the 10's complement of 52520. 10 is 105 to 52,524,7480. The number of digits in the number is n equals 5. 1. The 10's complement or 0.3267. 10 is 0.3267 is equal to 0.6733. 10 Chapter 1 No integer part, so 10 n equals 100 equals 1. Equals the 10's complement of 25.639. 10 is 102 to 25.639 74.361. Equals the 2's complement of 100 1100. 2 is 2610. 100 1100. 2 1,101,100. 2010100. The 2's complement of 0.0110. 2 is 1 to 0.0110. 2 equals 0.1010. The 16's complement of 4b7. 16 is 163 4b7. 10 equals 1000 4b7. 16 equals B 49, 16. From the definition and the examples, it is clear that the tens complement of a decimal number can be formed by leaving all least significant zeros unchanged, subtracting the first non-zeroliest significant digit from 10, and then subtracting all other higher significant digits from 9. The twos complement can be formed by leaving all least significant zeros and the first non-zero digit unchanged, and then replacing L's by zeros and zeros by L's in all other higher significant digits. A third, simpler method for obtaining the R's complement is given after the definition of the RL/S complement. The R's complement of a number exists for any base R greater than but not equal to 1, and may be obtained from the definition given above. The examples listed here use numbers with R equals 10 decimal and R equals 2 binary because these are the two bases of most interest to us. The name of the complement is related to the base of the number used. For example, the RL/S complement of a number in base 11 is named the tens complement, since R1 is equal to 10 for R equals 11. 1.5.2 The R1/S complement. Given a positive number n in base R with an integer part of n digits and a fraction part of m digits, the RL/S complement of n is defined as Rn, Rm, n. Some numerical examples follow. Equals the nines complement of 52520. 10 is 105 to 1. 52520, 99,999.50, 2,524, 7,479. No fraction part, so 10m equals 100 equals 1. The nines complement of 0.3267. 10 is 110 to 4, 0.3267. 0.9999 to 0.3267, 0.6732. No integer part, so 10 n equals 101. Equals the nines complement of 25.639. L0 is 102, 10 to 3, 25.639, 99.999, 25.639, 74.360. Equals the L's complement of 100, 1,100. 2 is open parenthesis 26 minus 1 close parenthesis minus open parenthesis 100, 1,100 close parenthesis 111,111 minus 100, 1,100. 20,100,11. Equals the L's complement of 0.0110. 2 is 1, 2 to 4. L0. 0.0110. 2, 0.1111 to 0.0110. 2, 0.1001. The sevens complement of 76. 8 is 8280. 10,768 equals 63. 10,768 equals 7776. 8 equals 18. From the examples, we see that the nines complement of a decimal number is formed simply by subtracting every digit from 9. The L's complement of a binary number is even simpler to form. The L's are changed to zeros and the zeros to L's. Since the R/T/S complement is very easily obtained, it is sometimes convenient to use it when the R's complement is desired. From the definitions and from a comparison of the results obtained in the examples, it follows that the R's complement can be obtained from the RL/S complement after the addition of Rm to the least significant digit. For example, the 2's complement of 10110,100 is obtained from the L's complement 0100111 by adding 1 to give 0100110.
Binary System 11. It is worth mentioning that the complement of the complement restores the number.
It is worth mentioning that the complement of the complement restores the number to its original value. The R's complement of n is Rn, n, and the complement of Rn, n is Rn. Rn n equals n, and similarly for the L's complement. 1.5.3 Subtraction with R's complements. The direct method of subtraction taught in elementary schools uses the borrow concept. In this method, we borrow a 1 from a higher significant position when the minuend digit is smaller than the corresponding subtrahend digit. This seems to be easiest when people perform subtraction with paper and pencil. When subtraction is implemented by means of digital components, this method is found to be less efficient than the method that uses complements and addition as stated below. The subtraction of two positive numbers m, n, both of base r, may be done as follows. 1. Add the minuend m to the r's complement of the subtrahend n. 2. Inspect the result obtained in step 1 for an end carry. A. If an end carry occurs, discard it. B. If an end carry does not occur, take the r's complement of the number obtained in step 1 and place a negative sign in front. The following examples illustrate the procedure. Example 1 to 5. Using 10's complement, subtract 72,532 to 3,250. M equals 72,532, 72,532, n equals 0, 3250 plus 10's complement of n equals 96,750, 96,750, and carry 169282. Answer 69,282. Example 1 to 6. Subtract 3,250 to 72,532. L0. M equals 0, 3250, n equals 72,532. 10's complement of n equals 27,468 plus 0, 3250, 27468. No carry 30718. Answer 69,282 equals 10's complement of 30,718. 12 Chapter 1 Example 1 to 7. Use 2's complement to perform m, n with the given binary numbers. M equals A101, 0100, 0100, n equals 100, 0100 plus 2's complement of n equals 011, 1100, 011, 1100, and carry 1001. 0000. Answer 10,000 B. M equals 100, 0100, 100, 0100, and equals 101, 0100 plus 2's complement of n equals 010, 1100, 010, 1100, no carry 111, 0000. Answer 10,000 equals 2's complement of 111, 0000. The proof of the procedure is, the addition of m to the r's complement of n gives m plus r and n. For numbers having an integer part of n digits, Rn is equal to a 1 in the n plus l position, what has been called the end carry. Since both m and n are assumed to be positive, then plus Rna, m, n, Rn if m greater than or equal to n, or b, m plus Rn, Rn if m less than n. In case A, the answer is positive and equal to m, n, which is directly obtained by discarding the end carry Rn. In case B, the answer is negative and equal to dash n m. This case is detected from the absence of an end carry. The answer is obtained by taking a second complement and adding a negative sign, plus Rn equals Rn, m, n, n, m. 1.5.4 Subtraction with R1, S complement. The procedure for subtraction with a RL, S complement is exactly the same as the one used with the R's complement except for one variation called end-around carry, as shown below. The subtraction of m, n, both positive numbers and base r, may be calculated in the following manner. 1. Add the minuend m to the RL, S complement of the subtrahend n. 2. Inspect the result obtained in step 1 for an end carry. A. If an end carry occurs, add 1 to the least significant digit, end-around carry. B. If an end carry does not occur, take the RL, S complement of the number obtained in step 1 and place a negative sign in front. The proof of this procedure is very similar to the one given for the R's complement case, and is left as an exercise. The following examples illustrate the procedure. Binary System 13 Example 1 to 8. Repeat examples 1 to 5 and 1 to 6 using 9's complements. M equals A 72,532 72,532 N equals 0 3250 of N equals 96,749 plus 9's complement 96,749 end around carry. 69282 answer 69,282 M equals B 0 3250 0 3250 N equals 72,532 N equals 27,467 plus 9's complement of 27,467 no carry 30717 answer 69,282 equals 9's complement of 30717 169,280 plus 1. Example 1 to 9. Repeat example 1 is equal to 7 using L's complement. M equals A 101, 0100 101, 0100 and equals 100, 0100 and equals 011, 1011 plus L's complement of 011, 1011 end around carry. 001, 0000 answer. 10,000 M equals B 100, 0100 100, 0100 and equals plus 101, 0100 L's complement of N equals 010, 101110, 1011 no carry 110, 1111 answer. 10,000 equals L's complement of 110, 1111, 1000, 1111 plus 1. 1.5.5 Comparison between 1's and 2's complements. A comparison between L's and 2's complements reveals the advantages and disadvantages of each. The L's complement has the advantage of being easier to implement by digital components, since the only thing that must be done is to change zeros into L's and L's into zeros. The implementation of the 2's complement may be obtained in two ways. 1. By adding 1 to the least significant digit of the L's complement, and 2. By leaving all leading zeros in the least significant positions and the first one unchanged. And only then changing all L's into zeros and all zeros into L's. During subtraction of 14 Chapter 1. Two numbers by complements. The 2's complement is advantageous in that only one arithmetic addition operation is required. The L's complement requires two arithmetic additions when an end-around carry occurs. The L's complement has the additional disadvantage of possessing two arithmetic zeros, one with all zeros and one with all L's. To illustrate this fact, consider the subtraction off the two equal binary numbers 1,100 minus 1,100 is equal to 0. Using L's complement, 1,100 plus 0, 0, 1, 1 plus 11, 11 complement again to obtain dash 0, 0, 0, 0. Using 2's complement, 1,100 plus 0, 100 plus 0, 0, 0, 0. While the 2's complement has only one arithmetic zero, the L's complement 0 can be positive or negative, which may complicate matters. Complements, very useful for arithmetic manipulations in digital computers, are discussed more in chapters 8 and 9. However, the L's complement is also useful in logical manipulations, as will be shown later, since the change of L's to zeros and vice versa is equivalent to a logical inversion operation. The 2's complement is used only in conjunction with arithmetic applications. Consequently, it is convenient to adopt the following convention. When the word complement, without mention of the type, is used in conjunction with a non-arithmetic application, the type is assumed to be the L's complement. 1.6 Binary Codes. Electronic digital systems use signals that have two distinct values and circuit elements that have two stable states. There is a direct analogy among binary signals, binary circuit elements, and binary digits. A binary number of n digits, for example, may be represented by n binary circuit elements, each having an output signal equivalent to a 0 or a 1. Digital systems represent and manipulate not only binary numbers, but also many other discrete elements of information. Any discrete element of information distinct among a group of quantities can be represented by a binary code. For example, red is one distinct color of the spectrum. The letter A is one distinct letter of the alphabet. A bit, by definition, is a binary digit. When used in conjunction with a binary code, it is better to think of it as denoting a binary quantity equal to 0 or 1. To represent a group of two and distinct elements in a binary code requires a minimum of n bits. This is because it is possible to arrange n bits in two and distinct ways. For example, a group of four distinct quantities can be represented by a 2-bit code, with each quantity assigned one of the following bit combinations: 0, 0, 0, 1, 10. 11. A group of 8 elements requires a 3-bit code, with each element assigned to 1 and only one of the following: 0, 0, 0, 0, 0, 1, 0, 10, 0, 11, 100, 101, 110, 111. The examples show that the distinct bit combinations of an n-bit code can be found by counting in binary from 0 to 2n1. Some bit combinations are unassigned when the number of elements of the group to be coded. Binary System 15 Table 1. 2 binary codes for the decimal digits decimal, BCD. Biquinary, digit 8421XS, 3 February 1st, 84 2421 504, 3210000000, 0011, 0000, 000010, 0001100001, 0100, 0111, 00011010, 001020, 010. 0101, 0110, 001010, 0100 30011, 0110, 0101, 00111010, 1000 40100, 0111, 0100, 01000011, 000050101, 1000, 1011, 1011100, 000160110, 1001, 1010, 11001000, 001070111, 1010, 1001, 11011000, 0100810000, 1011, 1000, 1110, 100, 100091001, 1100, 1111, 111101, 0000 is not a multiple of the power of 2. The 10 decimal digits 0, 1, 2, 9 are an example of such a group. A binary code that distinguishes among 10 elements must contain at least 4 bits. 3 bits can distinguish a maximum of 8 elements. 4 bits can form 16 distinct combinations, but since only 10 digits are coded, the remaining 6 combinations are unassigned and not used. Although the minimum number of bits required to code 2n distinct quantities is n, there is no maximum number of bits that may be used for a binary code. For example, the 10 decimal digits can be coded with 10 bits, and each decimal digit assigned a bit combination of 9 zeros and a 1. In this particular binary code, the digit 6 is assigned the bit combination 000, 100, 0000, 1.6.1 decimal codes. Binary codes for decimal digits require a minimum of 4 bits. Numerous different codes can be obtained by arranging 4 or more bits in 10 distinct possible combinations. A few possibilities are shown in Table 1, 2. The BCD, binary coded decimal, is a straight assignment of the binary equivalent. It is possible to assign weights to the binary bits according to their positions. The weights in the BCD code are 8, 4, 2, 1. The bit assignment 0110, for example, can be interpreted by the weights to represent the decimal digit 6 because 0 times 8 plus 1 times 4 plus 1 times 2 plus 0 times 1 is equal to 6. It is also possible to assign negative weights to a decimal code, as shown by the 8, 4, 2, 1 code. In this case, the bit combination 0110 is interpreted as the decimal digit 2, as obtained from 0 times 8 plus 1 by 4 plus 1 times, minus 2 plus 0 times, L equals 2. Two other weighted codes shown in the table are the 2421 and the 5043210. A decimal code that has been used in some old computers is the XS3 code. This is an unweighted code. Its code assignment is obtained from the corresponding value of BCD after the addition of 3. Numbers are represented in digital computers either in binary or in decimal through Alphanumeric code. When specifying data, the user likes to give the data in decimal form. The input decimal numbers are stored internally in the computer by means of a decimal code. Each decimal digit requires at least 4 binary storage elements. The decimal numbers are converted to binary when arithmetic operations are done internally with numbers represented in binary. It is also possible to perform the arithmetic operations directly in decimal with all numbers left uncoded. 16 Chapter 1. Form throughout. For example, the decimal number 395, when converted to binary, is equal to 11001011 and consists of 9 binary digits. The same number, when represented internally in the BCD code, occupies 4 bits for each decimal digit, for a total of 12 bits, 001110010101. The first 4 bits represent a 3, the next 4 a 9, and the last 4 a 5. It is very important to understand the difference between conversion of a decimal number to binary and the binary coding of a decimal number. In each case, the final result is a series of bits. The bits obtained from conversion are binary digits. Bits obtained from coding are combinations of L's and zeros arranged according to the rules of the code used. Therefore, it is extremely important to realize that a series of L's and zeros in a digital system may sometimes represent a binary number and at other times represent some other discrete quantity of information as specified by a given binary code. The BCD code, for example, has been chosen to be both a code and a direct binary conversion, as long as the decimal numbers are integers from 0 to 9. For numbers greater than 9, the conversion and the coding are completely different. This concept is so important that it is worth repeating with another example. The binary conversion of decimal 13 is 1101. The coding of decimal 13 with BCD is 00010011. From the 5 binary codes listed in Table 1, 2, the BCD seems the most natural to use and is indeed the one most commonly encountered. The other 4-bit codes listed have only characteristics in common that is not found in BCD. The XS, 3, the 2, 4, 2, 1, and the 8, 4, 2, 1 are self-complementary codes, that is, the 9's complement of the decimal number is easily obtained by changing L's to zeros and zeros to L's. For example, the decimal 395 is represented in the 2, 4, 2, 1 code by 001111111011. Its 9's complement 604 is represented by 10000000100, which is easily obtained from the replacement of L's by zeros and zeros by L's. This property is useful when arithmetic operations are internally done with decimal numbers in a binary code, and subtraction is calculated by means of 9's complement. The biquinary code shown in Table 1, 2 is an example of a 7-bit code with error detection properties. Each decimal digit consists of 5 zeros and 2 L's placed in the corresponding weighted columns. The error detection property of this code may be understood if one realizes that digital systems represent binary 1 by one distinct signal and binary 0 by a second distinct signal. During transmission of signals from one location to another, an error may occur. One or more bits may change value. A circuit in the receiving side can detect the presence of more, or less, than two L's and, if the received combination of bits does not agree with the allowable combination, an error is detected. 1.6.2 Error Detection Codes. Binary information, be it pulse-modulated signals or digital computer input or output, may be transmitted through some form of communication medium, such as wires or radio waves. Any external noise introduced into a physical communication medium changes bit values from 0 to 1 or vice versa. An error detection code can be used to detect errors during transmission. The detected error cannot be corrected, but its presence is indicated. The usual procedure is to observe the frequency of errors. If errors occur only once in a while, at random, and without a pronounced effect on the overall information transmitted, then either nothing is done or the particular erroneous message is transmitted again. If errors occur so often as to distort the meaning of the received information, the system is checked for malfunction. A parity bit is an extra bit included with a message to make the total number of L's either odd or even. A message of 4 bits and a parity bit, P, are shown in Table 1.3. In A, P is chosen so. Binary Systems 17 Table 1, 3 Parity Bit Generation. A. Message P, odd. B. Message P, even. 11000 1 1000 0 1000 1 1000 1 1 1000 1 0 1000 10 1 1000 10 0 1000 11 0 1000 11 1 1100 1 1100 0 11 0 1 0 11 0 1 1 11 10 0 11 10 1 11 11 1 11 11 0. That the sum of all L's is odd in all 5 bits. In B, P is chosen so that the sum of all L's is even. During transfer of information from one location to another, the parity bit is handled as follows. In the sending end, the message, in this case the first 4 bits, is applied to a parity generation network where the required P bit is generated. The message, including the parity bit, is transferred to its destination. In the receiving end, all the incoming bits, in this case 5, are applied to a parity check network to check the proper parity adopted. An error is detected if the checked parity does not correspond to the adopted one. The parity method detects the presence of 1, 3, or any odd combination of errors. An even combination of errors is undetectable. Further discussion of parity generation and checking can be found in Sector 4 to 9. 1.6.3 The Reflected Code. Digital systems can be designed to process data in discrete form only. Many physical systems supply continuous output data. These data must be converted into digital or discrete form before they are applied to a digital system. Continuous or analog information is convened into digital form by means of an analog-to-digital converter. It is sometimes convenient to use the reflected code shown in Table 1 to represent the digital data converted from the analog data. The advantage of the reflected code over pure binary numbers is that a number in the reflected code changes by only 1 bit as it proceeds from one number to the next. A typical application of the reflected code occurs when the analog data are represented by a continuous change of a shaft position. The shaft is partitioned into segments and each segment is assigned a number. If adjacent segments are made to correspond to adjacent reflected code numbers, ambiguity is reduced when 18 Chapter 1 Table 1, For 4-bit reflected code decimal equivalent 000000110012001103011104011501016010711601010. One 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 zero 11 1000 10 12 1011 13 1001 14 1015. Detection is sensed in the line that separates any two segments. The reflected code shown in Table 1 4 is only one of many possible such codes. To obtain a different reflected code, one can start with any bit combination and proceed to obtain the next bit combination by changing only one bit from 0 to 1 or 1 to 0 in any desired random fashion, as long as two numbers do not have identical code assignments. The reflected code is also known as the gray code. 1.6.4 Alphanumeric Codes. Many applications of digital computers require the handling of data that consist not only of numbers, but also of letters. For instance, an insurance company with millions of policyholders may use a digital computer to process its files. To represent the policyholder's name in binary form, it is necessary to have a binary code for the alphabet. In addition, the same binary code must represent decimal numbers and some other special characters. An alphanumeric, sometimes abbreviated alphanumeric, code is a binary code of a group of elements consisting of the 10 decimal digits, the 26 letters of the alphabet, and a certain number of special symbols such as $. The total number of elements in an alphanumeric group is greater than 36. Therefore, it must be coded with a minimum of 6 bits. 26 is equal to 64, but 25 is equal to 32 is insufficient. One possible arrangement of a 6-bit alphanumeric code is shown in Table 1, 5 under the name Internal Code. With a few variations, it is used in many computers to represent alphanumeric characters internally. The need to represent more than 64 characters, the lowercase letters and special control characters for the transmission of digital information, gave rise to 7- and 8-bit alphanumeric codes. One such code is known as ASCII, American Standard Code for Binary System 19 Table 1, 5 alphanumeric character codes, 6-bit, 7-bit, 8-bit, 12-bit character internal code, ASCII code, EBCD code, card code, A010001, 100, 000, 1 1100 000 112, 1B010 010 100 0010 1100. 0010 12,2 C 010 011 100 0011 1100
0010 12,2 C 010 011 100 0011 1100 0011 12,3 D 010 100 100 0100 1100 0100 12,4 E 010 101 100 0101 1100 0101 12,5 F 010 110 100 0110 1100 0110 12,6 G 010 111 100 0111 1100 0111 12,7 H 011 000 100 1000 1100 1012, 8 I 011 001 100 1001 1100 1001 12,9 J 100 001 100 1010 1100 and 1000 111, 1 K 100 010 100 1011 1100 and 100 10 2 L 100 011 100 1100 1100 and 100 11.3 M 100 100 100 1101 1100 and 100 11 4 N 100 100 and 100 1110 1100 and 1010 11.50 100 110 100 111111101111111111 1111 101 00011101111111111 101 0000101 00011111111 8 R 101 001 101 001011001 1001 9 S 110 010 101 0011 1110 00100, 2 T 110 011 101 0100 1110 00110, 3 U 110 100 101 0101 1110 01000, 4 V 110 101 101 0110 1110 01010, 5 W 110 110 101 0111 1110 01100, 6 X 110 111 101 1000 1110 01110, 7 Y 111 000 100 110 1110 1000, 8 Z 111 001 101 1010 1110 1000 and 10, 9 00000000011 0000 1111 0000000100001 011 0001 1111 00001 20000010 011 0010 1111 0010230000011 011 0011 1111 0011340000100 011 0100 1111 0100450000101 011 0101 1111 01015600010 011 0110 1111 01106 20 Chapter 17000111 011 0111 1111 0117800100011 1000 1111 10890001 011 1001 1111 1001 blank 110 0000010 0000010000000 no punch 011 011 010 11100010 1011 12, 8, 3 111 100 010 1000 0100 1101 12, 8, 5 plus 010 0000010 101 10 100 1110 12, 8, 6 101 $011 010 01000101 1011 11, 8, 3 asterisk 101 100 010 10100010 1111 8, 4 011 100 010 1001010 1101 11, 8, 5 100 0000010 11011011000011 slash 110 001 010 111011000010, 111 011 010 1100111011 0, 8, 3 equals 0010111 011 1101011110 8, 6. Information interchange. Another is known as EBCDIC, Extended BCD Interchange Code. The ASCII code listed in Table 1 to 5 consists of 7 bits but is, for all practical purposes, an 8-bit code because an 8th bit is invariably added for parity. When discrete information is transferred through punch cards, the alphanumeric characters use a 12-bit binary code. A punch card consists of 80 columns and 12 rows. In each column, an alphanumeric character I represented B holes punched in the appropriate rows. A hole is sensed as a 1 and the absence of a hole is sensed as a 0. The 12 rows are marked, starting from the top, as the 12, 11, 0, 1, 2, 9 punch. The first 3 are called the zone punch and the last 9 are called the numeric punch. The 12-bit card code shown in Table 1 to 5 lists the rows where a hole is punched, giving the LS. The remaining unlisted rows are assumed to be zeros. The 12-bit card code is inefficient with respect to the number of bits used. Most computers translate the input code into an internal 6-bit code. As an example, the internal code representation of the name John Doe is 100,001 100,000 110 JOHN blank D. OE 1.7 Binary storage and registers. The discrete elements of information in a digital computer must have a physical existence in some information storage medium. Furthermore, when discrete elements of information are represented in binary form, the information storage medium must contain binary storage elements for storing individual bits. A binary cell is a device that possesses 2 stable states and is capable of storing 1 bit of information. The input to the cell receives excitation signals that set it to one of the 2 states. The output of the cell is a physical quantity that distinguishes between the 2 states. The information stored in a cell is a 1 when it is in one stable state and a 0 when in the other stable state. Examples of binary cells are electronic flip-flop circuits, ferrite cores used in memories, and positions punched with a hole or not punched in a card. Binary System 21 1.7.1 Registers. A register is a group of binary cells. Since a cell stores 1 bit of information, it follows that a register with n cells can store any discrete quantity of information that contains n bits. The state of a register is an n-tuple number of LS and zeros, with each bit designating the state of one cell in the register. The content of a register is a function of the interpretation given to the information stored in it. Consider, for example, the following 16-cell register: 1100001111001001. 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. Physically, one may think of the register as composed of 16 binary cells, with each cell storing either a 1 or a 0. Suppose that the bit configuration stored in the register is as shown. The state of the register is the 16-tuple number 1100001111001001. Clearly, a register with n cells can be in one of 2 n possible states. Now, if one assumes that the content of the register represents a binary integer, then obviously the register can store any binary number from 0 to 216-1. For the particular example shown, the content of the register is the binary equivalent of the decimal number 50,121. If it is assumed that the register stores alphanumeric characters of an 8-bit code, the content of the register is any 2 meaningful characters. Unassigned bit combinations do not represent meaningful information. In the EBCDIC code, the above example represents the 2 characters C, left 8 bits, and I, right 8 bits. On the other hand, if one interprets the content of the register to be 4 decimal digits represented by a 4-bit code, the content of the register is a 4-digit decimal number. In the XS3 code, the above example is the decimal number 9096. The content of the register is meaningless in BCD since the bit combination 1100 is not assigned to any decimal digit. From this example, it is clear that a register can store 1 or more discrete elements of information and that the same bit configuration may be interpreted differently for different types of elements of information. It is important that the user store meaningful information in registers and that the computer be programmed to process this information according to the type of information stored. 1.7.2 Register Transfer. A digital computer is characterized by its registers. The memory unit, Fig 1:1, is merely a collection of thousands of registers for storing digital information. The processor unit is composed of various registers that store operands upon which operations are performed. The control unit uses registers to keep track of various computer sequences. And every input or output device must have at least one register to store the information transferred to or from the device. An inter-register transfer operation, a basic operation in digital systems, consists of a transfer of the information stored in one register into another. Figure 1-2 illustrates the transfer of information among registers and demonstrates pictorially the transfer of binary information from a teletype keyboard into a register in the memory unit. The input teletype unit is assumed to have a keyboard, a control circuit, and an input register. Each time a key is struck, the control enters into the input register an equivalent 8-bit alphanumeric character code. We shall assume that the code used is the ASCII code with an odd parity 8th bit. The information from the input register is transferred into the 8 least significant cells of a processor register. After every transfer, the input register is cleared to enable the control to insert a new 8-bit code when the keyboard is struck again. Each 8-bit character transferred to the processor register is preceded by a shift. 22 Chapter 1 Memory Unit Memory Register John 01001010101010001100110011001110 Processor Unit 8 cells Processor Register Input Teletype Unit John Input Register Control Keyboard 8 cells Figure 1.2 Transfer of information with registers of the previous character to the next 8 cells on its left. When a transfer of 4 characters is completed, the processor register is full, and its contents are transferred into a memory register. The content stored in the memory register shown in Fig. 1-2 came from the transfer of the characters JOHN after the 4 appropriate keys were struck. To process discrete quantities of information in binary form, a computer must be provided with 1. Devices that hold the data to be processed and 2. Circuit elements that manipulate individual bits of information. The device most commonly used for holding data is a register. Manipulation of binary variables is done by means of digital logic circuits. Figure 1-3 illustrates the process of adding two 10-bit binary numbers. The memory unit, which normally consists of thousands of registers, is shown in the diagram with only 3 of its registers. The part of the processor unit shown consists of 3 registers, RL, R2, and R3. Together with digital logic circuits that manipulate the bits of RL and R2 and transfer into R3 a binary number equal to their arithmetic sum. Memory registers store information and are incapable of processing the 2 operands. However, the information stored in memory can be transferred to processor registers. Results obtained in processor registers can be transferred back into a memory register for storage until needed again. The diagram shows the contents of 2 operands transferred from 2 memory registers into RL and R2. The digital logic circuits produce the sum, which is transferred to register R3. The contents of R3 can now be transferred back to one of the memory registers. The last 2 examples demonstrated the information flow capabilities of a digital system in a very simple manner. The registers of the system are the basic elements for storing and holding the binary information. The digital logic circuits process the information. Digital logic circuits and their manipulative capabilities are introduced in the next section. The subject of registers and register transfer operations is taken up again in Chapter 8. Binary System 23 0000000000 Memory Unit Sum 0011100001 Operand 1 Operand 2 000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 binary addition figure 1.3 example of binary information processing 1.8 binary logic. Binary logic deals with variables that take on two discrete values and with operations that assume logical meaning. The two values the variables take may be called by different names, e.g., true and false, yes and no, etc. But for our purpose it is convenient to think in terms of bits and assign the values of 1 and 0. Binary logic is used to describe, in a mathematical way, the manipulation and processing of binary information. It is particularly suited for the analysis and design of digital systems. For example, the digital logic circuits of Fig 1 to 3 that perform the binary arithmetic are circuits whose behavior is most conveniently expressed by means of binary variables and logical operations. The binary logic to be introduced in this section is equivalent to an algebra called Boolean algebra. The formal presentation of a two-valued Boolean algebra is covered in more detail in Chapter 2. The purpose of this section is to introduce Boolean algebra in a heuristic manner and relate it to digital logic circuits and binary signals. 1.8.1 Definition of binary logic. Binary logic consists of binary variables and logical operations. The variables are designated by letters of the alphabet such as A, B, C, X, Y, Z, etc., with each variable having two and only two distinct possible values, 1 and 0. There are three basic logical operations, and, or, and not. 1 and, this operation is represented by a dot or by the absence of an operator. For example xy equals z or xy equals z is read x and y is equal to z. The logical operation and is interpreted to mean that z equals 1 if and only if x equals 1 and y equals 1, otherwise z equals 0. Remember that x, y, and z are binary variables and can be equal either to I or 0, and nothing else. 24 Chapter 1 Table 1 to 6 Truth tables of logical operations and or not xy 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 x and y x x 0 0 0 0 0 0 0 1 0 1 0 0 1 1 1 0 1 0 0 1 0 1 1 1 1 1 1 1. 2 or, this operation is represented by a plus sign. For example, x plus y equals z is read x or y is equal to z, meaning that z equals 1 if x equals 1 or if y equals 1 or if both x equals 1 and y equals 1. If both x equals 0 and y equals 0, then z equals 0. 3 not, this operation is represented by a prime, sometimes by a bar. For example, x equals z, or x equals z, is read x not is equal to z, meaning that z is what x is not. In other words, if x equals 1, then z equals 0, but if x equals 0, then z equals 1. Binary logic resembles binary arithmetic, and the operations and or have some similarity as to multiplication and addition, respectively. In fact, the symbols used for and or are the same as those used for multiplication and addition. However, binary logic should not be confused with binary arithmetic. One should realize that an arithmetic variable designates a number that may consist of many digits. A logic variable is always either a 1 or a 0. For example, in binary arithmetic we have 1 plus 1 equals 10, read, 1 plus 1 is equal to 2, while in binary logic we have 1 plus 1 equals 1, read, 1 or 1 is equal to 1. For each combination of the values of x and y, there is a value of z specified by the definition of the logical operation. These definitions may be listed in a compact form using truth tables. A truth table is a table of all possible combinations of the variables showing the relation between the values that the variables may take and the result of the operation. For example, the truth tables for the operations and or with variables x and y are obtained by listing all possible values that the variables may have when combined in pairs. The result of the operation for each combination is then listed in a separate row. The truth tables for and, or, and not are listed in Table 1 to 6. These tables clearly demonstrate the definitions of the operations. 1.8.2 Switching circuits and binary signals. The use of binary variables and the application of binary logic are demonstrated by the simple switching circuits of Fig. 1 to 4. Let the manual switches A and B represent two binary variables with values equal to 0 when the switch is open and 1 when the switch is closed. Similarly, let the lamp L represent a third binary variable equal to 1 when the light is on and 0 when off. For the switches in series, the light turns on if A and B are closed. For the switches in parallel, the light turns on if A or B is closed. It is obvious that the two circuits can be expressed by means of binary logic with the and or operations, respectively. L equals A. B for the circuit of Fig L4, A, L equals A plus B for the circuit of Fig L4, B. Binary system 25 LASABSBL voltage source S, A, switches in series logic N, B, switches in parallel logic or figure 1.4 switching circuits that demonstrate binary logic. Electronic digital circuits are sometimes called switching circuits because they behave like a switch. With the active elements such as a transistor either conducting, switch closed, or not conducting, switch open. Instead of changing the switch manually, an electronic switching circuit uses binary signals to control the conduction or non-conduction state of the active element. Electrical signals such as voltages or currents exist throughout a digital system in either one of two recognizable values, except during transition. Voltage-operated circuits, for example, respond to two separate voltage levels which represent a binary variable equal to logic 1 or logic 0. For example, a particular digital system may define logic 1 as a signal with a nominal value of 3 volts, and logic 0 as a signal with a nominal value of 0 volt. As shown in Fig. 1 to 5, each voltage level has an acceptable deviation from the nominal. The intermediate region between the allowed regions is crossed only during stale transitions. The input terminals of digital circuits accept binary signals within the allowable tolerances and respond at the output terminal with binary signals that fall within the specified tolerances. 1.8.3 Logic gates. Electronic digital circuits are also called logic circuits because, with the proper input, they establish logical manipulation paths. Any desired information for computing or control can be volts for. Nominal logic 1 nominal logic 0 transition occurs between these limits tolerance allowed for logic 1 tolerance allowed for logic 0 3210.5-0.50 figure 1.5 example of binary signals. 26 Chapter 1 xz equals x plus yy, b, 2 input or gate xz equals xyy a, 2 input and gate, c, not gate or inverter BAG equals A plus B plus C plus D DCF equals ABCCBA. D. 3 input and gate, E. 4 input or gate figure 1.6 symbols for digital logic circuits. Operated upon by passing binary signals through various combinations of logic circuits, each signal representing a variable and carrying one bit of information. Logic circuits that perform the logical operations of and, or, and not are shown with their symbols in Fig 1 to 6. These circuits called gates, are blocks of hardware that produce a logic 1 or logic 0 output signal if input logic requirements are satisfied. Note that 4 different names have been used for the same type of circuits: digital circuits, switching circuits, logic circuits, and gates. All 4 names are widely used, but we shall refer to the circuits as and, or, and not gates. The not gate is sometimes called an inverter circuit since it inverts a binary signal. The input signals X and Y in the 2 input gates of Fig 1 to 6 may exist in one of 4 possible states, 0, 0, 10, 11, or 0, 1. These input signals are shown in Fig. 1 to 7, together with the output signals for the and or gates. The timing diagrams in Fig 1 to 7 illustrate the response of each circuit to each of the 4 possible input binary combinations. The reason for the name inverter for the NOT gate is apparent from a comparison of the signal X, input of inverter, and that of X, output of inverter. An AND OR gates may have more than 2 inputs. An AND gate with 3 inputs and an OR gate with 4 inputs are shown in Fig 1 to 6. The 3-input AND gate responds with a logic 1 output if all 3 input signals are logic 1. The output produces a logic 0 signal if any input is logic 0. The 4-input OR gate responds with a logic 1 when any input is a logic 1. Its output becomes logic 0 if all input signals are logic 0. The mathematical system of binary logic is better known as Boolean, or switching algebra. This algebra is conveniently used to describe the operation of complex networks of digital circuits. Designers of digital systems use Boolean algebra to transform circuit diagrams to algebraic expressions and vice versa. Chapters 2 and 3 are devoted to the study of Boolean algebra, its properties, and manipulative capabilities. Chapter 4 shows how Boolean algebra may be used to express mathematically the interconnections among networks of gates. 1.9 Integrated circuits. Digital circuits are invariably constructed with integrated circuits. An integrated circuit, abbreviated IC, is a small silicon semiconductor crystal, called a chip, containing electrical components such as transistors, diodes, resistors, and capacitors. The various components are interconnected inside the chip to form an electronic circuit. The chip is mounted on a metal or plastic package, and connections are welded to external pins to form the IC. Integrated circuits differ from other electronic circuits composed of detachable components in that individual components in the IC. Binary System 27x0110y001110n, xy00100 or, x and y01110 not, x10011 Figure 1.7 Input-output signals for gates, A, B, and C, of Fig 1.6. Cannot be separated or disconnected, and the circuit inside the package is accessible only through the external pins. Integrated circuits come in two types of packages, the flat package and the dual inline, DIP, package, as shown in Fig 1-8. The dual inline package is the most widely used type because of the low price and easy installation on circuit boards. The envelope of the IC package is made of plastic or ceramic. Most packages have standard sizes, and the number of pins ranges from 8 to 64. Each IC has a numeric designation printed on the surface of the package for identification. Each vendor publishes a data book or catalog that provides the necessary information concerning the various products. The size of IC packages is very small. For example, 4N gates are enclosed inside a 14-pin dual inline package with dimensions of 20 x 8 x 3 mm. An entire microprocessor is enclosed within a 40-pin dual inline package with dimensions of 50 x 15 x 4 mm. Besides a substantial reduction in size, ICs offer other advantages and benefits compared to electronic circuits with discrete components. The cost of ICs is very low, which makes them economical to use. Their reduced power consumption makes the digital system more economical to operate. They have a high reliability against failure, so the digital system needs less repairs. The operating speed is higher, which makes them suitable for high-speed operations. The use of ICs reduces the number of external wiring connections because many of the connections are internal to the package. Because of all these advantages, digital systems are always constructed with integrated circuits. Integrated circuits are classified in two general categories, linear and digital. Linear ICs operate with continuous signals to provide electronic functions such as amplifiers and voltage. Flat package dual inline package Figure 1.8 Integrated circuit packages. 28 Chapter 1 Comparators. Digital integrated circuits operate with binary signals and are made up of interconnected digital gates. Here we are concerned only with digital integrated circuits. As the technology of ICs has improved, the number of gates that can be put on a single silicon chip has increased considerably. The differentiation between those ICs that have a few internal gates and those having tens or hundreds of gates is made by a customary reference to a package as being either a small, medium, or large-scale integration device. Several logic gates in a single package make it a small-scale integration, SSI, device. To qualify as a medium-scale integration, MSI, device, the IC must perform a complete logic function and have a complexity of 10 to 100 gates. A large-scale integration, LSI, device performs a logic function with more than 100 gates. There are also very large-scale integration, VLSI, devices that contain thousands of gates in a single chip. Many diagrams of digital circuits considered throughout this book are shown in detail up to the individual gates and their interconnections. Such diagrams are useful for demonstrating the logical construction of a particular function. However, it must be realized that, in practice, the function may be obtained from an MSI or LSI device, and the user has access only to external inputs and outputs but not to inputs and outputs of intermediate gates. For example, a designer who wants to incorporate a register in his system is more likely to choose such a function from an available MSI circuit instead of designing it with individual digital circuits as may be shown in a diagram. References 1. Richard, R.K., Arithmetic Operations in Digital Computers. New York, Van Nostrand Co., 1955. 2 Flores, I. The Logic of Computer Arithmetic. Englewood Cliffs, N.J., Prentice Hall, Inc., L963. 3 Chu, Y., Digital Computer Design Fundamentals. New York, McGraw-Hill Book Co., 1962, Chaps. 1 and 2. 4 Kostopoulos, G.K., Digital Engineering. New York, John Wiley & Sons, Inc., 1975, Chap 1. 5 Rhine, V.T., Fundamentals of Digital Systems Design. Englewood Cliffs, N.J., Prentice Hall. Inc., 1973, Chap. 1. Problems 1-1. Write the first 20 decimal digits in base 3. 1-2. Add and multiply the following numbers in the given base without convening to decimal. A. 1230, 4 and 23, 4, B. 135.4, 6 and 43.2, 6, C. 367, 8 and 715, 8, D. 296, 12 and 57, 12 1-3. Convert the decimal number 250.5 to base 3, base 4, base 7, base 8, and base 16. 1-4 Convert the following decimal numbers to binary, 12.0625, 104, 673.23, and 1998.
Convert the decimal number 250.5 to base 3, base 4, base 7, base 8, and base 16. 1-4. Convert the following decimal numbers to binary, 12.0625, 104, 673.23, and 1998. 1-5. Convert the following binary numbers to decimal, 10.10001, 101,110.0101, 1,110,101.110, 1,101,101.111. Binary system 29 1-6. Convert the following numbers from the given base to the bases indicated. A. Decimal 225.225 to binary, octal, and hexadecimal. B. Binary 11,010,111.110 to decimal, octal, and hexadecimal. C. Octal 623.77 to decimal, binary, and hexadecimal. D. Hexadecimal 2AC5, D to decimal, octal, and binary 1-7. Convert the following numbers to decimal. A. 1001001.01L, 2 E. 0.3426b, 121213f, 57c, 1032.24g, 8.39d, 4310, 5, h, 198, 12 Obtain the L's and 2's complement of the following binary numbers: 101, 0101, 011, 1000, 000, 0001, 10,000, 00000, 1-9. Obtain the nines and tens complement of the following decimal numbers: 13579, 09900, 90090, 10,000, 00000. 1 to 10. Find the tens complement of 935, 11 1 to 11. Perform the subtraction with the following decimal numbers using 1, tens complement, and 2, nines complement. Check the answer by straight subtraction. E. 5,250 to 321. C. 753 to 864. F. 3,570 to 2,100. D. 20 to 1,001 to 12. Perform the subtraction with the following binary numbers using 1, 2's complement, and 2, L's complement. Check the answer by straight subtraction. A. 11010, 1101. C. 10010, 10011. B. 11010, 10000. D. 100 to 110,001 to 13. Prove the procedure stated in Sector 1 to 5 for the subtraction of two numbers with RL, S complement. 1 to 14. For the weighted codes A 3, 3, 2, 1 and B 4, 4, 3, 2 for the decimal digits, determine all possible tables so that the nines complement of each decimal digit is obtained by changing L's to zeros and zeros to L's. 1 to 15. Represent the decimal number 8620, A in BCD, B in excess, 3 code, C in 2, 4, 2, 1 code, and D as a binary number. 1 to 16. A binary code uses 10 bits to represent each of the 10 decimal digits. Each digit is assigned a code of 9 zeros and a 1. The code for digit 6, for example, is 000, 100, 0000. Determine the binary code for the remaining decimal digits. 1 to 17. Obtain the weighted binary code for the base 12 digits using weights of 5,421. 1 to 18. Determine the odd parity bit generated when the message consists of the 10 decimal digits in the 8, 4, 2, 1 code. 1 to 19. Determine two other combinations for a reflected code other than the one shown in Table 1, 4. 1 to 20. Obtain a binary code to represent all base 6 digits so that the 5's complement is obtained by zeros and zeros by ones in the bits of the code. 1 to 21. Assign a binary code in some orderly manner to the 52 playing cards. Use the minimum number of bits. 1 to 22. Write your first name, middle initial, and last name in an 8-bit code made up of the 7 ASCII bits of Table 1, 5, and an even parity bit in the most significant position. Include blanks between names and a period after the middle initial. 30 Chapter 1. 1 to 23 show the bit configuration of a 24-cell register when its content represents A. The number 295, 10 in binary, B. The decimal number 295 in BCD, and C. The characters XY5 in EBCDIC. 1 to 24. The state of a 12-cell register is 0101100101111. What is its content if it represents A. 3 decimal digits in BCD, B. 3 decimal digits in XS, 3 code, C. 3 decimal digits in 2, 4, 2 I code, and D. 2 characters in the internal code of Table 1, 5. 1 to 25 show the contents of all registers in Figure 1. 3 if the two binary numbers added have the decimal equivalent of 257 and 1050. Assume registers with 11 cells. 1 to 26. Express the following switching circuit in binary logic notation. A, B, L, C, S voltage source 1 to 27. Show the signals by means of a diagram similar to Figure 1, 7. Of the outputs F and G in Figure 1, 6. Use arbitrary binary signals for the inputs A, B, C, and D. 1 to 28. Explain switch equivalent circuits of NOT, NAND, NOR, XOR, and XNOR. 1 to 29, convert following into octal, BC 5A16, 10,101,011.1101, 2, 765.54, 10 to 30. Write short notes on digital computer, number system, complements, error detection code, reflected code, register transfer, integrated circuits. 1 to 31. Perform -44, 10, 67, 10 using 10's complement method. 2.1 Basic definitions. A Boolean algebra, like any other deductive mathematical system, may be defined with a set of elements, a set of operators, and a number of unproved axioms or postulates. A set of elements is any collection of objects having a common property. If S is a set, and X and Y are certain objects, then X is an element of S denotes that X is a member of the set S, and Y is not an element of S denotes that Y is not an element of S. A set with a denumerable number of elements is specified by braces, equals 1, 2, 3, 4, i.e., the elements of set A are the numbers 1, 2, 3, and 4. A binary operator defined on a set S of elements is a rule that assigns to each pair of elements from S a unique element from S. As an example, consider the relation A** B equals C. We say that asterisk is a binary operator if it specifies a rule for finding C from the pair B, and also if A, B, C is an element of S. However, asterisk is not a binary operator if A, B is an element of S, while the rule find C is not an element of S. The postulates of a mathematical system form the basic assumptions from which it is possible to deduce the rules, theorems, and properties of the system. The most common postulates used to formulate various algebraic structures are: 1. Closure. A set S is closed with respect to a binary operator if, for every pair of elements of S, the binary operator specifies a rule for obtaining a unique element of S. For example, the set of natural numbers n equals 1, 2, 3, 4 is closed with respect to the binary operator plus by the rules of arithmetic addition, since for any a, b is an element of n we obtain a unique c is an element of n by the operation a plus b equals c. The set of natural numbers is not closed with respect to the binary operator minus symbol by the rules of arithmetic subtraction because 2 minus 3 equals -1 and 2, 3 is an element of n, while -1 is not an element of n. 2. Associative law. A binary operator asterisk on a set S is said to be associative whenever x asterisk equals z is an element of sy asterisk z x asterisk y asterisk z for all x, y. 3. Commutative law. A binary operator asterisk on a set S is said to be commutative whenever y equals y is an element of s x asterisk y asterisk x for all x. 4. Identity element. A set S is said to have an identity element with respect to a binary operation asterisk on S if there exists an element E is an element of S with the property x equals E equals XX is an element of S E asterisk x asterisk for every. 32 Chapter 2 Example. The element 0 is an identity element with respect to operation plus on the set of integers I equals -3, -2, -1, 0, 1, 2, 3. Since x plus 0 is equal to 0 plus x equals x for any x is an element of I. The set of natural numbers n has no identity element since 0 is excluded from the set. 5. Inverse. A set S having the identity element E with respect to a binary operator asterisk is said to have an inverse whenever, for every x is an element of S, there exists an element y is an element of S, such that x asterisk y equals E. E equals example. In the set of integers I with 0, the inverse of an element is A since A plus A equals 0. 6. Distributive law. If asterisk and are two binary operators on a set S, asterisk is said to be distributive over whenever x asterisk y is z equals x asterisk y, x asterisk z. An example of an algebraic structure is a field. A field is a set of elements, together with two binary operators, each having properties 1 to 5, and both operators combine to give property 6. The set of real numbers together with the binary operators plus and form the field of real numbers. The field of real numbers is the basis for arithmetic and ordinary algebra. The operators and postulates have the following meanings. The binary operator plus defines addition. The additive identity is 0. The additive inverse defines subtraction. The binary operator defines multiplication. The multiplicative identity is 1. A equals the multiplicative inverse of 1 slash a defines division, i.e., a 1 slash a equals 1. The only distributive law applicable is that of over plus c equals a, b plus a, c. 2.2 Axiomatic definition of Boolean algebra. In 1854, George Boole 1. introduced a systematic treatment of logic and developed for this purpose an algebraic system, now called Boolean algebra. In 1938, C.E. Shannon, 2. introduced a two-valued Boolean algebra called switching algebra, in which he demonstrated that properties of by stable electrical switching circuits can be represented by this algebra. For the formal definition of Boolean algebra, we shall employ the postulates formulated by E.V. Huntington, 3, in 1904. These postulates or axioms are not unique for defining Boolean algebra. Other sets of postulates have been used. Boolean algebra is an algebraic structure defined on a set of elements *c, for example, Birkhoff and Barty 4. Chapter 5. Boolean algebra and logic gates 33b together with two binary operators plus and are provided the following Huntington postulates are satisfied. 1. A. Closure with respect to the operator plus. B. Closure with respect to the operator plus 2. A. An identity element with respect to designated by 0x plus 0 is equal to 0 plus x equals x. 1 is equal to 1. B. An identity element with respect to designated by 1x, x equals x. 3. A. Commutative with respect to plus y equals y plus x. B. Commutative with respect to y equals y or x. Plus c equals 4. A is distributive over x plus xz. Plus x plus equals x plus b is distributive over y z, y, x plus z. X is an element of 5. For every element b, there exists an element x is an element of b, called the complement of x such that a, x plus x equals 1 and b, xx equals 0. Y pertenece a B6. There exists at least two elements x, such that x superscript 1 y. Comparing Boolean algebra with arithmetic and ordinary algebra, the field of real numbers, we note the following differences. 1. Huntington postulates do not include the associative law. However, this law holds for Boolean algebra and can be derived, for both operators, from the other postulates. Plus x plus equals x plus 2. The distributive law of over, i.e., y is z, y, x plus c, is valid for Boolean algebra but not for ordinary algebra. 3. Boolean algebra does not have additive or multiplicative inverses. Therefore, there are no subtraction or division operations. 4. Postulate 5 defines an operator called complement which is not available in ordinary algebra. 5. Ordinary algebra deals with the real numbers, which constitute an infinite set of elements. Boolean algebra deals with the as-yet undefined set of elements b, but in the two-valued Boolean algebra defined below, and of interest in our subsequent use of this algebra. B is defined as a set with only two elements, 0 and 1. Boolean algebra resembles ordinary algebra in some respects. The choice of symbols plus and is intentional to facilitate Boolean algebraic manipulations by persons already familiar with ordinary algebra. Although one can use some knowledge from ordinary algebra to deal with Boolean algebra, the beginner must be careful not to substitute the rules of ordinary algebra where they are not applicable. It is important to distinguish between the elements of the set of an algebraic structure and the variables of an algebraic system. For example, the elements of the field of real numbers are numbers, whereas variables such as a, B, C, etc., used in ordinary algebra, are symbols that stand for real numbers. Similarly, in Boolean algebra, one defines the elements of the set B, and variables such as x, y, z are merely symbols that represent the elements. At this point, it is important to realize that in order to have a Boolean algebra, one must show 34 Chapter 2.1. The elements of a set B, 2. The rules of operation for the two binary operators, and 3. That the set of elements B, together with the two operators, satisfies the 6 Huntington postulates. One can formulate many Boolean algebras, depending on the choice of elements of B and the rules of operation. Asterisk in our subsequent work, we deal only with a two-valued Boolean algebra, i.e., one with only two elements. Two-valued Boolean algebra has applications in set theory, the algebra of classes, and in propositional logic. Our interest here is with the application of Boolean algebra to gate-type circuits. 2.2.2 Two-valued Boolean algebra. A two-valued Boolean algebra is defined on a set of two elements, B equals 0, 1, with rules for the two binary operators plus, and, as shown in the following operator tables, the rule for is for verification of postulate 5x, yx, yx, yx plus yx 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 1, 1, 1, 1, x, 1, 0. These rules are exactly the same as the and, or, and not operations, respectively, defined in Table 1, 6. We must now show that the Huntington postulates are valid for the set B equals 0, 1, and the two binary operators defined above. 1. Closure is obvious from the table since the result of each operation is either 1 or 0 and 1. 0 is an element of B. 2. From the tables we see that 0 plus 0 is equal to 0, 0 plus 1 minus 1 plus 0 is equal to 1. A. 1 is equal to 1, 0 is equal to 0, 1 is equal to 0. B. 1, 1, which establishes the two identity elements 0, 4 plus, and 1, 4, as defined by postulate 2. 3. The commutative laws are obvious from the symmetry of the binary operator tables. Plus C equals 4. A. The distribute law x, y plus xz can be shown to hold true from the operator tables by forming a truth table of all possible values of x, y, and z. For each combination, we derive x, y plus z, and show that the value is the same as x, y plus xz. Asterisk C, for example, Hone 6, Whitesett 7, or Birkhoff and Barty 4. Boolean algebra and logic gates 35x, y, z, y plus cx, y plus c, x, y, x, z, x, y plus x, z, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, 0, 0, 1, 1, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1. 0, 1, 1, 1, 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, b. The distributive law of plus over can be shown to hold true by means of a truth table similar to the one above. 5. From the complement table it is easily shown that x equals 0 equals a x plus 1, since 0 plus 0 plus 1 is equal to 1, and 1 plus 1 equals 1 plus 0 is equal to 1x equals 0, equals 0, 1 is equal to 0, 1 equals 1 b, x 0. Since 0 and 1 is 0 is equal to 0, which verifies postulate 5. 6. Postulate 6 is satisfied because the two-valued Boolean algebra has two distinct elements 1 and 0, with 1 superscript 1, 0. We have just established a two-valued Boolean algebra having a set of two elements, 1 and 0, two binary operators with operation rules equivalent to the and, or operations, and a complement operator equivalent to the not operator. Thus, Boolean algebra has been defined in a formal mathematical manner and has been shown to be equivalent to the binary logic presented heuristically in section 1 to 8. The heuristic presentation is helpful in understanding the application of Boolean algebra to gate-type circuits. The formal presentation is necessary for developing the theorems and properties of the algebraic system. The two-valued Boolean algebra defined in this section is also called switching algebra by engineers. To emphasize the similarities between two-valued Boolean algebra and other binary systems, this algebra was called binary logic in section 1 to 8. From here on, we shall drop the adjective two-valued from Boolean algebra in subsequent discussions. 2.3 Basic Theorems and Properties of Boolean Algebra. 2.3.1 Duality. The Huntington postulates have been listed in pairs and designated by part A and part B. One part may be obtained from the other if the binary operators and the identity elements are re-interchanged. This important property of Boolean algebra is called the duality principle. It states that every algebraic expression deducible from the postulates of Boolean algebra remains valid if the operators and identity elements are interchanged. In a two-valued Boolean algebra, the identity elements and the elements of the set B are the same, 1 and 0. The duality principle has many applications. If the dual of an algebraic expression is desired, we simply interchange or and operators and replace ones by zeros and zeros by ones. 36 Chapter 2 Table 2 1 Postulates and Theorems of Boolean Algebra. Postulate 2 A. X plus 0 equals x. B. X 1 equals x. Postulate 5 A. X plus x equals 1. B. X equals 0. Theorem 1 A. X plus x equals x. B. X equals x. Theorem 2 A. X plus 1 is equal to 1. B. X 0 is equal to 0. Theorem 3 Involution x equals x. Postulate 3 Commutative A. X plus y equals y plus x. B. xy equals yx. Theorem 4 Associative A. X plus y plus c equals x plus y plus c. B. xyz equals xyz. Postulate 4 Distributive A. X y plus c equals xy plus xc. B. X plus yz equals x plus y, x plus c. Theorem 5 De Morgan A. X plus y equals x, y. B. xy equals x plus y. Theorem 6 Absorption A. X plus xy equals x. B. xx plus y equals x. 2.3.2 Basic Theorems. Table 2 1 lists 6 theorems of Boolean algebra and 4 of its postulates. The notation. Omitting the whenever this does not lead to confusion. The theorems and postulates listed are the most basic relationships in Boolean algebra. The reader is advised to become familiar with them as soon as possible. The theorems, like the postulates, are listed in pairs. Each relation is the dual of the one paired with it. The postulates are basic axioms of the algebraic structure and need no proof. The theorems must be proven from the postulates. The proofs of the theorems with one variable are presented below. At the right is listed the number of the postulate which justifies each step of the proof. Theorem 1. X plus x equals x. X plus x equals x plus x, a 1 by postulate. 2b equals x plus x, x plus x. 5a equals x plus xx. 4b equals x plus 0. 5b equals x2. A. Theorem 1 Bx x equals x. X equals xx plus 0 by postulate. 2a equals xx plus xx. 5b equals xx plus x. 4a equals x1. 5a equals x2. B. Note that Theorem 1b is the dual of Theorem 1a and that each step of the proof in part B is the dual of part A. Any dual theorem can be similarly derived from the proof of its corresponding pair. Boolean algebra and logic gates. 37 Theorem 2 X plus 1 is equal to 1. X plus 1 is equal to 1. X plus 1 equals x plus x. X plus by postulate. 2b 1 5a equals x plus x. 1 4b equals x plus x. 2b equals 1 5a.
Theorem 2, Bx0 equals 0 by duality.
Theorem 2, Bx 0 is equal to 0 by duality. X equals x plus x equals 1x equals theorem 3x. From postulate 5, we have an x0, which defines the complement of x. The complement of x is x and is also x. Therefore, since the complement is unique, we have that x equals x. The theorems involving 2 or 3 variables may be proven algebraically from the postulates and the theorems which have already been proven. Take, for example, the absorption theorem. Theorem 6, ax plus xy minus x plus xy equals x, 1 plus by postulate 2, b, xy equals x, 1 plus y, by postulate 4, a equals x, y plus 1, by postulate 3, a equals x, 1 by theorem 2, a equals x by postulate 2, b. Theorem 6, b xx plus y equals x by duality. The theorems of Boolean algebra can be shown to hold true by means of truth tables. In truth tables, both sides of the relation are checked to yield identical results for all possible combinations of variables involved. The following truth table verifies the first absorption theorem. Equals xy x plus xy 0 0 0 0 0 1 0 0 1 0 0 1 1 1 1 1. The algebraic proofs of the associative law and de Morgan's theorem are long and will not be shown here. However, their validity is easily shown with truth tables. For example, the truth table for the first de Morgan's theorem, x plus y equals x, y is shown below. X, Y, X, Y, X, Y, X, Y, X, Y, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 0, 1.
For example, the truth table for the first de Morgan's theorem, x plus y equals x, y is shown below. X, Y, X, Y, X, Y, X, Y, X, Y, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1.
For example, the truth table for the first de Morgan's theorem, x plus y equals xy is shown below. Xy x and y, x and y, xy xy 0 0 1 1 0 1 0 1 0 1 1 1 1 0 0 0 1 1 0 0 1 0 1 0 0 0 0. 38 Chapter 2 2.3.3 Operator Precedence. The operator precedence for evaluating Boolean expressions is 1. Parenthesis, 2. Not, 3. And 4. Or. In other words, the expression inside the parenthesis must be evaluated before all other operations. The next operation that holds precedence is the complement, then follows the and finally the or. As an example, consider the truth table for De Morgan's theorem. The left side of the expression is x and y. Therefore, the expression inside the parenthesis is evaluated first and the result then complemented. The right side of the expression is xy. Therefore the complement of x and the complement of y are both evaluated first and the result is then and. Note that in ordinary arithmetic the same precedence holds, except for the complement, when multiplication and addition are replaced by an and or, respectively. Example 2 to 1, using basic Boolean theorem prove. A. X plus y, x plus z, equals x plus yz soln, x plus y, x plus z, equals xx plus xz plus yz since x equals x plus xz plus x plus yz equals x, 1 plus z, plus x plus yz since 1 plus z equals 1 equals x plus yz equals x, 1 plus y plus yz since 1 plus y equals 1 equals x plus yz, proved. Yz equals b xy plus xz plus yz soln. Xy plus xz plus yz equals xy, z plus xz, y plus y, yz, xx. X equals plus since x plus 1 plus equals xyz plus xyz plus xyz plus xyz plus xyz equals xyz plus xyz plus xyz plus xyz since xyz plus xyz equals xyz plus xyz plus xyz plus xyz rearranging. y, yz, xx, y equals x equals xz, y plus 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 since y plus 1 and x plus 1 equals xz plus yz, proved. 2.3.4 Venn diagram. A helpful illustration that may be used to visualize the relationships among the variables of a Boolean expression is the Venn diagram. This diagram consists of a rectangle such as shown. XY 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 Figure 2.1 Venn diagram for two variables. Boolean algebra and logic gates 39 XY Figure 2.2 Venn diagram illustration x equals xy plus x. Y in Fig 2:1, inside of which are drawn overlapping circles, one for each variable. Each circle is labeled by a variable. We designate all points inside a circle as belonging to the named variable and all points outside a circle as not belonging to the variable. Take, for example, the circle labeled x. If we are inside the circle, we say that x equals 1, when outside, we say x equals 0. Now, with two overlapping circles, there are four distinct areas inside the rectangle. The area not belonging to either x or y, xy, the area inside circle y but outside x, xy, the area inside circle x but outside, xy, and the area inside both circles, xy. Venn diagrams may be used to illustrate the postulates of Boolean algebra or to show the validity of theorems. Figure 2:2, for example, illustrates that the area belonging to xy is inside the circle x and therefore x plus xy equals x. Figure 2:3 illustrates the distributive law xy plus z equals xy plus xz. In this diagram we have three overlapping circles, one for each of the variables x, y, and z. It is possible to distinguish 8 distinct areas in a three-variable Venn diagram. For this particular example, the distributive law is demonstrated by noting that the area intersecting the circle x with the area enclosing y or z is the same area belonging to xy or xz. 2.4 Boolean functions. A binary variable can take the value of 0 or 1. A Boolean function is an expression formed with binary variables, the two binary operators or n, the unary operator not, parenthesis, and equal sign. For a given value of the variables, the function can be either 0 or 1. Consider, for example, the Boolean function, f1 equals xyz. X equals 1, y equals 1, z equals. The function f1 is equal to 1 if n 1, otherwise f1 0. The above is an example of a Boolean function represented as an algebraic expression. A Boolean function may also be represented in a truth table. To represent a function in a truth table, we need a list of the two n combinations of ls and zeros of the n binary variables, and a column showing the combinations xyz, xyz, xy and z, xy and xz. Figure 2.3 Venn diagram illustration of the distributive law. 40 Chapter 2 Table 2:2 Truth tables for f1 equals xyz, f2 equals x plus yz, f3 equals xyz plus xyz plus xy, and f4 equals xy plus xz xyz f1 f2 f3 f4 0 0 0 0 0 0 0 0 0 1 0 1 1 1 0 1 0 0 0 0 0 0 1 1 0 0 1 1 1 0 0 0 1 1 1 1 0 1 0 1 1 1 1 1 0 1 1 0 0 1 1 1 0 1 0 0, for which the function is equal to 1 or 0. As shown in Table 2:2, there are 8 possible distinct combinations for assigning bits to three variables. The column labeled f1 contains either a 0 or a 1 for each of these combinations. The table shows that the function f1 is equal to 1 only when x equals 1, y equals 1, and z, 0. It is equal to 0 otherwise. Note that the statement z equals 1 is equivalent to saying that z equals 0. Consider now the function, f2, x and yz equals 1 x equals 1 y equals z equals x equals 1 f2 if or if 0, while 1. In Table 2:2, in the last 4 rows and yz equals 0 1 in rows 0 0 1 and 101. The latter combination applies also for x equals 1. Therefore, there are 5 combinations that make f2 equals 1. As a third example, consider the function f3 equals xyz plus xyz plus xy. This is shown in table 2-2 with 4 ls and 4 zeros. f4 is the same as f3 and is considered below. Any Boolean function can be represented in a truth table. The number of rows in the table is 2n.
Any Boolean function can be represented in a truth table. The number of rows in the table is 2n, where n is the number of binary variables in the function. The ones and zeros combinations for each row is easily obtained from the binary numbers by counting from 0 to 2n1. For each row of the table, there is a value for the function equal to either 1 or 0. The question now arises, is an algebraic expression of a given Boolean function unique? In other words, is it possible to find two algebraic expressions that specify the same function? The answer to this question is yes. As a matter of fact, the manipulation of Boolean algebra is applied mostly to the problem of finding simpler expressions for the same function. Consider, for example, the function f4 equals xy plus xz. From table 2, we find that f4 is the same as f3 since both have identical ones and zeros for each combination of values of the three binary variables. In general, two functions of n binary variables are said to be equal if they have the same value for all possible 2n combinations of the n variables. A Boolean function may be transformed from an algebraic expression into a logic diagram composed of and, or, and not gates. The implementation of the four functions introduced in Boolean algebra and logic gates 41xyz f1x f2yz yz b f2 a f1 equals xyz equals x plus xy f3z c f3 equals x yz plus x yz plus xy xyz f4. Figure 2.4 Implementation of Boolean function with gates d f4 equals xy plus xc. The previous discussion is shown in Figure 2.4. The logic diagram includes an inverter circuit for every variable present in its complement form. The inverter is unnecessary if the complement of the variable is available. There is an AND gate for each term in the expression, and an OR gate is used to combine two or more terms. From the diagrams, it is obvious that the implementation of f4 requires fewer gates and fewer inputs than f3. Since f4 and f3 are equal Boolean functions, it is more economical to implement the f4 form than the f3 form. To find simpler circuits, one must know how to manipulate Boolean functions to obtain equal and simpler expressions. What constitutes the best form of a Boolean function depends on the particular application. In this section, consideration is given to the criterion of equipment minimization. 2.4.1 Algebraic manipulation. A literal is a primed or unprimed variable. When a Boolean function is implemented with logic gates, each literal in the function designates an input to a gate, and each term is implemented with a gate. The minimization of the number of literals and the number of terms results in a circuit with less equipment. It is not always possible to minimize both simultaneously. Usually, further criteria must be available. At the moment, we shall narrow the minimization criterion to literal minimization. We shall discuss other criteria in Chapter 5. The number of literals in a Boolean function can be minimized by algebraic manipulations. Unfortunately, there are no specific rules to follow that will guarantee the final answer. The only method available is a cut and try. 42 Chapter 2 Procedure employing the postulates, the basic theorems, and any other manipulation method which becomes familiar with use. The following examples illustrate this procedure. Example 2-2. Simplify the following Boolean functions to a minimum number of literals. 1x más x y más x más y igual a 1.
Example 2-2. Simplify the following Boolean functions to a minimum number of literals. 1x plus xy plus x plus y, equals 1, x plus y, equals x plus y 2x, x plus y, equals xx plus xy equals 0 plus xy equals xy. 3xyz plus xyz plus xy equals xz, y plus xy equals xz plus xy plus xz plus yz equals xy plus xz plus 4. xyz, x plus x, equals xy plus xz plus xyz plus xyz equals xy, 1 plus z, plus xz, 1 plus y, equals xy plus xz. Plus, x plus z, equals, x plus 5. xy, z, yy, z, by duality from function 4. Functions 1 and 2 are the duals of each other and use dual expressions in corresponding steps. Function 3 shows the equality of the functions f3 and f4 discussed previously.
Functions 1 and 2 are the duals of each other and use dual expressions in corresponding steps. Function 3 shows the equality of the functions f3 and f4 discussed previously. The fourth illustrates the fact that an increase in the number of literals sometimes leads to a final simpler expression. Function 5 is not minimized directly, but can be derived from the dual of the steps used to derive function 4. 2.4.2 Complement of a function. The complement of a function f is f, and is obtained from an interchange of zeros for ones and l's for zeros in the value of f. The complement of a function may be derived algebraically through De Morgan's theorem. This pair of theorems is listed in Table 2, one for 2 variables. De Morgan's theorems can be extended to 3 or more variables. The 3-variable form of the first De Morgan's theorem is derived below. The postulates and theorems are those listed in Table 2, 1. A plus equals A plus B plus C, x, B plus C equals x. Let equals a x by Theorem 5, A, De Morgan equals a plus C, B plus C equals x, B substitute equals a BC by Theorem 5, A, De Morgan equals a BC by Theorem 4, B, associative. De Morgan's theorems for any number of variables resemble in form the 2-variable case and can be derived by successive substitutions similar to the method used in the above derivation. These theorems can be generalized as follows: A plus B plus C plus D plus F equals A B C D F. F equals A plus B plus C plus D plus F. Boolean algebra and logic gates 43. The generalized form of De Morgan's theorem states that the complement of a function is obtained by interchanging and/or operators and complementing each literal. Equals x, yz plus x, yz equals x. Example 2 to 3. Find the complement of the functions f1 and f2, yz plus yz. Applying De Morgan's theorem as many times as necessary, the complements are obtained as follows. Iguala, x más iguala, x, iguala, x, f1 y
equals, x plus equals, x equals, xf1 yz plus xyz, yz, xyz, y plus f2 equals x, yz plus yz, equals x plus, yz plus yz, equals x plus, yz, plus y plus z. Z, x, yz, equals x plus, y plus z, y plus z. A simpler procedure for deriving the complement of a function is to take the dual of the function and complement.
A simpler procedure for deriving the complement of a function is to take the dual of the function and complement each literal. This method follows from the generalized De Morgan's theorem. Remember that the dual of a function is obtained from the interchange of and/or operators and ones and zeros. Example 2 to 4. Find the complement of the functions f1 and f2 of example 2 to 3 by taking their duals and complementing each literal. 1. f1 equals x, yz, plus x, yz. The dual of f1 is x plus y plus c, x plus y plus c. Complement each literal. X plus y plus c, x plus y plus c, equals f1. Más y más dos. f2, x, y, z plus yz. The dual of f2 is x plus y plus c, y plus c. Complement each literal. xc, y plus c, equals f2. 2.5 canonical and standard forms, 2.5.1 minterms and max terms. A binary variable may appear either in its normal form, x, or in its complement form, x. Now consider two binary variables x and y combined with an AND operation. Since each variable may appear in either form, there are four possible combinations: xy, 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 and xy. Each of these four AND terms represents one of the distinct areas in the Venn diagram of Figure 2.1 and is called a minterm or a standard product. In a similar manner, n variables can be combined to form two n minterms. The two n different minterms may be determined by a method similar to the one shown in Table 2.3 for three variables. The binary numbers from 0 to 2n, are listed under the n variables. Each minterm is obtained from an n term of the n variables, with each variable being primed if the corresponding bit of the binary number is a 0 and imprinted if a 1. A symbol for each minterms is also shown in the table and is of the form mj, where j denotes the decimal equivalent of the binary number of the minterm designated. 44 Chapter 2 Table 2, 3 minterms and max terms for three binary variables: minterms, max terms, x, y, z, term designation 0, 0, 0, x, y, z, and 0 x plus y plus z m 0, 0, 0, 1 x, y, z, m1 x plus y plus z, m1. 0, 1, 0 x's, meter 2 x plus y plus meter
0, 1, 0 xyz m2 x and y and z m2 0, 1, 1 xyz m3 x and y and z m3 1, 0, 0 xyz m4 x and y and z m4 1, 0, 1 xyz m5 x and y and z m5 1, 1, 0 xyz m6 x and y and z m6 1, 1, 1 xyz m7 x and y and z m7. In a similar fashion, n variables forming an OR term, with each variable being primed or unprimed, provide 1, 2 n possible combinations, called maxterms or standard sums. The 8 maxterms for 3 variables, together with their symbolic designation, are listed in Table 2-3. Any 2 n maxterms for n variables may be determined similarly. Each maxterm is obtained from an OR term of the n variables, with each variable being unprimed if the corresponding bit is a 0 and primed if a 1 asterisk. Note that each maxterm is the complement of its corresponding minterm, and vice versa. A Boolean function may be expressed algebraically from a given truth table by forming a minterm for each combination of the variables which produces a 1 in the function, and then taking th of all those terms. For example, the function f1 in Table 2-4 is determined by expressing th combinations 0, 0, 1, 100, and 111 as xyz, xyz, and xyz, respectively. Since each one of these minterms results in f1 equals 1, we should have f1 equals xyz plus xyz plus m4 plus xyz equals m1 m7. Similarly, it may be easily verified that f2 equals xyz plus xyz plus xyz plus xyz equals m3 plus m5 plus m6 plus m7. These examples demonstrate an important property of Boolean algebra. Any Boolean function can be expressed as a sum of mjane terms. By sum is meant the O-ring of terms. Now consider the complement of a Boolean function. It may be read from the truth table by forming a minterm for each combination that produces a 0 in the function and then O-ring those terms. The complement of f1 is read as f1 equals xyz plus xyz plus xyz plus xyz plus xyz. Asterisk. Some books define a maxterm as an OR term of the n variables, with each variable being unprimed if the bit is a 1 and primed if a 0. The definition adopted in this book is preferable as it leads to simpler conversions between maxterm and minterm type functions. Boolean algebra and logic gates. 45 Table 2-4 functions of 3 variables xyz function f1 function f2 0 0 0 0 0 0 0 1 1 0 0 1 0 0 0 0 1 1 0 1 1 0 0 1 0 1 0 1 0 1 1 I 0 0 1 1 1 1 1 1. If we take the complement of f1, we obtain the function f1 equals x plus y plus z, xz, x plus y plus z, x plus y plus z, x plus y plus z, equals m0 m2 m3 m5 m6. Similarly, it is possible to read the expression for f2 from the table, z, x f2 equals, x plus y plus z, x plus y plus z, x plus y plus y plus z, equals m0 m1 m2 m4. These examples demonstrate a second important property of Boolean algebra. Any Boolean function can be expressed as a product of maxterms. By product is meant the ANDing of terms. The procedure for obtaining the product of maxterms directly from the truth table is as follows. Form a maxterm for each combination of the variables which produces a zero in the function and then form the n of all those maxterms. Boolean functions expressed as a sum of minterms or product of maxterms are said to be in canonical form. 2.5.2 Sum of minterms. It was previously stated that for n binary variables, one can obtain two n distinct minterms, and that any Boolean function can be expressed as a sum of minterms. The minterms whose sum defines the Boolean function are those that give the LS of the function in a truth table. Since the function can be either 1 or 0 for each minterm, and since there are two n minterms, one can calculate the possible functions that can be formed with n variables to be 2n. It is sometimes convenient to express the Boolean function in its sum of minterms form. If not in this form, it can be made so by first expanding the expression into a sum of n terms. Each term is then inspected to see if it contains all the variables. If it misses one or more variables, it is ANDed with an expression such as x and x, where x is one of the missing variables. The following example clarifies this procedure. 46 Chapter 2. Example 2-5, express the Boolean function f equals a plus bc in a sum of minterms. The function has three variables a, b, and c. The first term a is missing two variables, therefore, a equals a, b plus b, equals ab plus ab. This is still missing one variable. A equals ab, c plus c, plus ab, c plus c, equals abc plus abc plus abc plus abc. The second term bc is missing one variable, bc equals bc, a plus a, equals abc plus abc. Combining all terms, we have f equals a plus bc equals ab.
F equals A plus BC equals ABC plus ABC, plus ABC plus ABC, plus ABC plus ABC. But ABC appears twice, and according to Theorem 1, x plus x equals x, it is possible to remove one of them. Rearranging the minterms in ascending order, we finally obtain F equals ABC plus ABC, plus ABC plus ABC, plus ABC equals M1 plus M4 plus M5 plus M6 plus M7. It is sometimes convenient to express the Boolean function, when in its sum of minterms, in the following short notation. F, A, B, C, equals sigma, 1, 4, 5, 6, 7. The summation symbol sigma stands for the ORing of terms. The numbers following it are the minterms of the function. The letters in parentheses following F form a list of the variables in the order taken when the minterm is converted to an n term. 2.5.3 Product of maxterms. Each of the 22 n functions of n binary variables can be also expressed as a product of maxterms. To express the Boolean function as a product of maxterms, it must first be brought into a form of or terms. This may be done by using the distributive law x plus yz equals x plus y, x plus c. Then any missing variable x in each or term is ORed with xx. This procedure is clarified by the following example. Boolean algebra and logic gates 47 Example 2-6 express the Boolean function f equals xy plus xc in a product of maxterm form. First, convert the function into or terms using the distributive law. F equals xy plus xc equals xy plus equals x plus x, y plus x, x plus x, xy plus cz, y plus c equals x plus y, x plus c, y plus c. the function has three variables x, y, and z. Each or term is missing one variable, therefore, x plus y equals x plus y plus zz equals x plus y plus z, x plus y plus z. X plus c equals x plus c plus y equals x plus y plus c, x plus y plus c, y plus c equals y plus c plus xx equals x plus y plus c, x plus y plus c. Combining all the terms and removing those that appear more than once, we finally obtain f equals x plus y plus c, x plus y plus c, x plus y plus c, x plus y plus c equals m0, m2, m4, m5. A convenient way to express this function is as follows. F, x, y, z equals pi 0, 2, 4, 5. The product symbol, pi, denotes the andying of max terms. The numbers are the max terms of the function. 2.5.4 Conversion between canonical forms. The complement of a function expressed as the sum of minterms equals the sum of minterms missing from the original function. This is because the original function is expressed by those minterms that make the function equal to I, while its complement is a 1 for those minterms that the function is a 0. As an example, consider the function f a b c equals sigma 1, 4, 5, 6, 7. This has a complement that can be expressed as equals sigma f a b c 0, 2, 3 equals m0 plus m2 plus m3. Now, if we take the complement of f by De Morgan's theorem, we obtain f in a different form, equals pi f equals m0 plus m2 plus m3 equals m0, m2, m3 equals m0, m2, m3, 0, 2, 3. The last conversion follows from the definition of minterms and max terms as shown in Table 2, 3. From the table, it is clear that the following relation holds true: mj equals mj. That is, the max term with subscript j is a complement of the minterm with the same subscript j, and vice versa. 48, Chapter 2. The last example demonstrates the conversion between a function expressed in sum of minterms and its equivalent in product of max terms. A similar argument will show that the conversion between the product of max terms and the sum of minterms is similar. We now state a general conversion procedure. To convert from one canonical form to another, interchange the symbols sigma and pi and list those numbers missing from the original form. As another example, the function f x y z equals pi 0, 2, 4, 5 is expressed in the product of max term form. Its conversion to sum of minterms is f x y z equals sigma 1, 3, 6, 7. Note that, in order to find the missing terms, one must realize that the total number of minterms or max terms is 2n, where n is the number of binary variables in the function. 2.5.5 Standard Forms. The two canonical forms of Boolean algebra are basic forms that one obtains from reading a function from the truth table. These forms are very seldom the ones with the least number of literals, because each minterm or max term must contain, by definition, all the variables either complemented or uncomplemented. Another way to express Boolean functions is in standard form. In this configuration, the terms that form the function may contain 1, 2, or any number of literals. There are two types of standard forms: the sum of products and product of sums. The sum of products is a Boolean expression containing n terms, called product terms, of one or more literals each. The sum denotes the ORing of these terms. An example of a function expressed in sum of products is f1 equals y plus xyz. The expression has three product terms of 1, 2, and 3 literals each, respectively. Their sum is an effect n or operation. A product of sums is a Boolean expression containing OR terms, called sum terms. Each term may have any number of literals. The product denotes the ending of these terms. An example of a function expressed in product of sums is f2 equals xy plus c, x plus y plus c plus w. This expression has three sum terms of 1, 2, and 4 literals each. The product is an AND operation. The use of the words product and sum stems from the similarity of the AND operation to the arithmetic product, multiplication, and the similarity of the OR operation to the arithmetic sum, addition. A Boolean function may be expressed in a non-standard form. For example, the function equals AB plus CD, AB plus CD, F3, is neither in sum of products nor in product of sums. It can be changed to a standard form by using the distributive law to remove the parentheses. Equals ABCD plus F3 ABC'd. Boolean algebra and logic gates 49 Table 2. 5 truth tables for the 16 functions of 2 binary variables x, y, f0, f1, f2, f3, f4, f5, f6, f7, f8, f9, f10, f11, f12, f13, f14, f15, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 1. 0 1 0 0 0 0 1 1 1 1 0 0 0 0 1 1 1 1 1 0 0 0 1 1 0 0 1 1 0 0 1 1 0 0 1 1 1 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 0 1 operator symbol / circle plus plus subset of superset of 2.6 other logic operations. When the binary operators and or are placed between two variables x and y, they form two Boolean functions x, y, and x plus y, respectively. It was stated previously that there are 22 n functions for n binary variables. For two variables n equals 2, and the number of possible Boolean functions is 16, therefore, the and or functions are only 2 of a total of 16 possible functions formed with two binary variables. It would be instructive to find the other 14 functions and investigate their properties. The truth tables for the 16 functions formed with two binary variables x and y are listed in Table 2, 5. In this table, each of the 16 columns F0 to F15 represents a truth table of one possible function for the two given variables x and y. Note that the functions are determined from the 16 binary combinations that can be assigned to F. Some of the functions are shown with an operator symbol. For example, F1 represents the truth table for and F7 represents the truth table for or. The operator symbols for these functions are and, plus, respectively. The 16 functions listed in truth table form can be expressed algebraically by means of Boolean expressions. This is shown in the first column of Table 2, 6. The Boolean expressions listed are simplified to their minimum number of literals. Although each function can be expressed in terms of the Boolean operators and, or, and not, there is no reason one cannot assign special operator symbols for expressing the other functions. Such operator symbols are listed in the second column of Table 2, 6. However, all the new symbols shown, except for the exclusive OR symbol circle plus, are not in common use by digital designers. Each of the functions in Table 2, 6 is listed with an accompanying name and a comment that explains the function in some way. The 16 functions listed can be subdivided into 3 categories. 1. 2 functions that produce a constant 0 or 1. 2. 4 functions with unary operations complement and transfer. 3. 10 functions with binary operators that define 8 different operations and or, NAND, NOR, exclusive OR, equivalence, inhibition, and implication. Any function can be equal to a constant, but a binary function can be equal to only 1 or 0. The complement function produces the complement of each of the binary variables. A function which is equal to an input variable has been given the name transfer, because the variable x or y is transferred through the gate that forms the function without changing its value. Of the 8 binary operators, 2, inhibition and implication, are used by logicians but are seldom used in 50 Chapter 2 Table 2, 6 Boolean expressions for the 16 functions of two variables. Boolean functions operator symbol name comments f0 equals 0 null binary constant 0 f1 equals xy and x and y f2 equals xy. X/y inhibition x, but not y f3 equals x transfer xf for equals xy y/x inhibition y, but not x f5 equals y transfer y f6 equals xy plus xy x circle plus y use of or x or y, but not both f7 equals x plus y or x or y. F8 equals x plus y. Xy nor not or f9 equals xy plus xy. Xy equivalence asterisk x equals y f10 equals y. Y complement not y f11 equals x plus y. X subset of y implication if y then x f12 equals x. X complement not x. F13 equals x plus yx superset of y implication if x then y f14 equals xy. Xy NAND not and f15 equals 1 identity binary constant 1 asterisk equivalence is also known as equality, coincidence, and exclusive NOR. Computer logic. The and or operators have been mentioned in conjunction with Boolean algebra. The other four functions are extensively used in the design of digital systems. The NOR function is the complement of the OR function, and its name is an abbreviation of not OR. Similarly, NAND is the complement of and is an abbreviation of not AND. The exclusive OR, abbreviated XOR or YOR, is similar to OR but excludes the combination of both X and Y being equal to 1. The equivalence is a function that is 1 when the two binary variables are equal, i.e., when both are 0 or both are 1. The exclusive OR and equivalence functions are the complements of each other. This can be easily verified by inspecting Table 2, 5. The truth table for the exclusive OR is F6 and for the equivalence is F9, and these two functions are the complements of each other. For this reason, the equivalence function is often called exclusive NOR, i.e., exclusive OR not. Boolean algebra, as defined in sections 2 to 2, has two binary operators, which we have called and or, and a unary operator, not complement. From the definitions, we have deduced a number of properties of these operators and now have defined other binary operators in terms of them. There is nothing unique about this procedure. We could have just as well started with the operator NOR, for example, and later defined and, or, and not in terms of it. There are, nevertheless, good reasons for introducing Boolean algebra in the way it has been introduced. The concepts of and, or, and not are familiar and are used by people to express everyday logical ideas. Moreover, the Huntington postulates reflect the dual nature of the algebra, emphasizing the symmetry of plus and with respect to each other. Boolean algebra and logic gates. 51 2.7 Digital logic gates. Since Boolean functions are expressed in terms of and, or, and not operations, it is easier to implement a Boolean function with these types of gates. The possibility of constructing gates for the other logic operations is of practical interest. Factors to be weighed when considering the construction of other types of logic gates are 1. The feasibility and economy of producing the gate with physical components. 2. The possibility of extending the gate to more than two inputs. 3. The basic properties of the binary operator such as commutativity and associativity. And 4. The ability of the gate to implement Boolean functions alone or in conjunction with other gates. Of the 16 functions defined in Table 2, 6, 2 are equal to a constant and 4 others are repeated twice. There are only 10 functions left to be considered as candidates for logic gates. 2. Inhibition and implication are not commutative or associative and thus are impractical to use as standard logic gates. The other 8, complement, transfer, and or, NAND, NOR, exclusive, or, and equivalence, are used as standard gates in digital design. The graphic symbols and truth tables of the 8 gates are shown in Figure 2, 5. Each gate has one or two binary input variables designated by X and Y, and one binary output variable designated by F. The AND, OR, and inverter circuits were defined in Figure 1, 6. The inverter circuit inverts the logic sense of a binary variable. It produces the not or complement function. The small circle in the output of the graphic symbol of an inverter designates the logic complement. The triangle symbol by itself designates a buffer circuit. A buffer produces the transfer function, but does not produce any particular logic operation, since the binary value of the output is equal to the binary value of the input. This circuit is used merely for power amplification of the signal and is equivalento to inverters connected in cascade. The NAND function is the complement of the AND function, as indicated by a graphic symbol which consists of an AND graphic symbol followed by a small circle. The NOR function is the complement of the OR function and uses an OR graphic symbol followed by a small circle. The NAND and NOR gates are extensively used as standard logic gates and are in fact far more popular than the AND and OR gates. This is because NAND and NOR gates are easily constructed with transistor circuits, and because Boolean functions can be easily implemented with them. The exclusive OR gate has a graphic symbol similar to that of the OR gate, except for the additional curved line on the input side. The equivalence, or exclusive NOR, gate is the complement of the exclusive OR, as indicated by the small circle on the output side of the graphic symbol. 2.7.1 Extension to multiple inputs. The gates shown in Figure 2.5, except for the inverter and buffer, can be extended to have more than two inputs. A gate can be extended to have multiple inputs if the binary operation it represents is commutative and associative. The and OR operations, defined in Boolean algebra, possess these two properties. For the OR function, we have x plus y equals y plus x commutative and x plus y plus c equals x plus y plus c equals x plus y plus c associative, which indicates that the gate inputs can be interchanged and that the OR function can be extended to three or more variables. 52 Chapter 2 Name graphic symbol algebraic function truth table and xyff equals xy0011x01011y0001f or xyff equals x plus y0011x0101y0111 f equals x inverter x0110xf. F igual a x buffer x f0101x y f010111000111x y f NAND f igual a xy.
F equals x buffer x f0101 x y f010111100011 x y f NAND f equals x y f010110000011 x y, NOR f equals x plus fy xy f010101100011. Exclusive OR xf equals xy plus xy equals xyf, xor, yxyf exclusive NOR xfyf equals xy plus xy00 or equals xy equivalence 0101100011 Figure 2.5 Digital Logic Gates. Boolean Algebra and Logic Gates 53 xyz, xy, z equals x plus y, z xyz, yz, xx, y plus z. Figure 2.6 demonstrating the non-associativity of the NOR operator, xy, z is not equal to xyz. The NAND and NOR functions are commutative and their gates can be extended to have more than two inputs, provided the definition of the operation is
The NAND and NOR functions are commutative and their gates can be extended to have more than two inputs, provided the definition of the operation is slightly modified. The difficulty is that the NAND and NOR operators are not associative, i.e., xyz is not equal to xyz, as shown in Figure 2.6 and below. Igual a x más xy, z igual a x más y más z.
Equals x plus xy, z equals. The NAND and NOR functions are commutative and their gates can equals x plus xy, z equals x plus y plus zy, z equals xz plus yzx, yz equals x plus y plus z, x, y plus z, xy plus xz. To overcome this difficulty, we define the multiple NOR, or NAND, gate as a complemented OR, or AND, gate. Thus, by definition, we have xyz equals x plus y plus z, xyz equals xyz. The graphic symbols for the three input gates are shown in Fig 2-7. In writing cascaded NOR and NAND operations, one must use the correct parentheses to signify the proper sequence of the gates. To demonstrate this, consider the circuit of Fig 2-7, c. The Boolean function for the circuit must be written as f equals abc, day, abc plus day. The second expression is obtained from De Morgan's theorem. It also shows that an expression in sum of products can be implemented with NAND gates. Further discussion of NAND and NOR gates can be found in sections 3-6, 4-7, and 4-8. XZY, XXYZ plus Y plus Z, XYZ, A, 3-input NOR gate, B, 3-input NAND gate F equals, ABC, day, equals ABC plus day. ADEBC, C, cascaded NAND gate figure 2.7 multiple input and cascaded NOR and NAND gate. 54 Chapter 2 FXYZ equals XYZ, A, using two input gates, B, a 3-input gate XYZ F0000111001100101010101010101001. C, truth table figure 2.83 input exclusive OR gate. The exclusive OR and equivalence gates are both commutative and associative and can be extended to more than two inputs. However, multiple input exclusive OR gates are uncommon from the hardware standpoint. In fact, even a two-input function is usually constructed with other types of gates. Moreover, the definition of these functions must be modified when extended to more than two variables. The exclusive OR is an odd function, i.e., it is equal to 1 if the input variables have an odd number of ones. The equivalence function is an even function, i.e., it is equal to 1 if the input.
The equivalence function is an even function, i.e., it is equal to 1 if the input variables have an even number of zeros. The construction of a 3-input exclusive OR function is shown in Figure 2.8. It is normally implemented by cascading two input gates as shown in A. Graphically, it can be represented with a single 3-input gate as shown in B. The truth table in C clearly indicates that the output F is equal to 1 if only one input is equal to 1 or if all three inputs are equal to 1, i.e., when the total number of ones in the input variables is odd. Further discussion of exclusive OR and equivalence can be found in section 4-9. Example 2-7. Construct and gate using NOR gate soln, A to B equals A B equals A plus B. Using De Morgan's theorem y equals A plus B equals A, B 2.8 IC digital logic families. The IC was introduced in section 1-9, where it was stated that digital circuits are invariably constructed with ICs. Having discussed various digital logic gates in the previous section, we are now in a position to present IC gates and discuss their general properties. Boolean algebra and logic gates 55. Digital IC gates are classified not only by their logic operation, but also by the specific logic circuit family to which they belong. Each logic family has its own basic electronic circuit upon which more complex digital circuits and functions are developed. The basic circuit in each family is either a NAND or a NOR gate. The electronic components employed in the construction of the basic circuit are usually used to name the logic family. Many different logic families of digital ICs have been introduced commercially. The ones that have achieved widespread popularity are listed below. TTL transistor logic, ECL emitter-coupled logic, MOS metal oxide semiconductor, CMOS complementary metal oxide semiconductor. I2L integrated injection logic. TTL has an extensive list of digital functions and is currently the most popular logic family. ECL is used in systems requiring high-speed operations. MLES and I2L are used in circuits requiring component density, and CMOS is used in systems requiring low power consumption. The analysis of the basic electronic circuit in each logic family is presented in Chapter 13. The reader familiar with basic electronics can refer to Chapter 13 at this time to become acquainted with these electronic circuits. Here we restrict the discussion to the general properties of the various IC gates available commercially. Because of the high density with which transistors can be fabricated in MOS and I2L, these two families are mostly used for LSI functions. The other three families, TTL, ECL, and CMOS, have LSI devices and also a large number of MSI and SSI devices. SSI devices are those that come with a small number of gates or flip-flops, presented in Section 6.2, in one IC package. The limit on the number of circuits in SSI devices is the number of pins in the package. A 14-pin package, for example, can accommodate only 4 two-input gates. Because each gate requires 3 external pins, 2 each for inputs and 1 each for output, for a total of 12 pins. The remaining 12 pins are needed for supplying power to the circuits. Some typical SSI circuits are shown in Figure 2.9. Each IC is enclosed within a 14 or 16-pin package. The pins are numbered along the two sides of the package and specify the connections that can be made. The gates drawn inside the ICs are for information only and cannot be seen because the actual IC package appears as shown in Figure 1.8. TTL ICs are usually distinguished by numerical designation as the 5400 and 7400 series. The former has a wide operating temperature range, suitable for military use, and the latter has a narrower temperature range, suitable for industrial use. The numeric designation of the 7400 series means that IC packages are numbered as 7400, 7401, 7402, etc. Some vendors make available TTL ICs with different numerical designations, such as the 9000 or the 8000 series. Figure 2-9a shows two TTL SSI circuits. The 7404 provides 6 hex inverters in a package. The 7400 provides 4 quadruple 2-input NAND gates. The terminals marked VCC and GND are the power supply pins which require a voltage of 5 volts for proper operation. The most common ECL type is designated as the 10,000 series. Figure 2-9b shows two ECL circuits. The 10102 provides 4 2-input NOR gates. Note that an ECL gate may have 2 outputs, one for the NOR function and another for the OR function. Pin 9 of the 10102 IC. The 10107 IC provides 3 exclusive OR gates. Here again there are 2 outputs from each gate. The 56 Chapter 2 VCC 9 14 13 12 11 10 7404 hex inverters VCC 2 12 34 56 14 13 12 11 10 9 8 8 7 GND A. TTL gates VCC 2 123 4 567 GND 7400 quadruple 2 input NAND gates 16 15 14 13 12 16 15 14 13 11 10 12 11 10 9 12 34 5 678 2 3 4 5 6 7 8 9 1 1 8 V VCC 1 VCC 1 and CV 10100 2 quadruple 2 input NOR gates 10107 triple exclusive OR / NOR gates B ECL gates 1312 VDD 8 NC 14 NC 13 12 11 9 10 NC 16 14 10 15 11 9 1 2 3 4 5 6 7 1 2 3 6 7 4 5 VSS VDD NC 4000 and 2 dual 4 input NOR gates 4050 hex buffers CMOS gates. Figure 2.9 Some typical integrated circuit gates. Boolean algebra and logic gates 57 logic value signal value logic value signal value 1 H0 H0 L1 L A positive logic B negative logic figure 2.10 signal amplitude assignment and type of logic. Other output gives the exclusive NOR function or equivalence. ECL gates have 3 terminals for power supply. VCC1 and VCC2 are usually connected to ground, and VE to a 5.2 volt supply. CMOS circuits of the 4000 series are shown in Fig. 2-9c. Only two 4-input NOR gates can be accommodated in the 4002 because of pin limitation. The 4050 type provides 6 buffer gates. Both ICs have 2 unused terminals marked NC, no connection. The terminal marked VDD requires a power supply voltage from 3 to 15 volts, while VSS is usually connected to ground. 2.8.1 Positive and negative logic. The binary signal at the inputs or output of any gate can have one of two values, except during transition. One signal value represents logic, 1, and the other, logic, 0. Since two signal values are assigned to two logic values, there exist two different assignments of signals to logic. Because of the principle of duality of Boolean algebra, an interchange of signal value assignment results in a dual function implementation. Consider the two values of a binary signal as shown in Figure 2.10. One value must be higher than the other since the two values must be different in order to distinguish between them. We designate the higher level by H and the lower level by L. There are two choices for logic value assignment. Choosing the high level H to represent logic 1, as shown in Fig. 2-10a, defines a positive logic system. Choosing the low-level L to represent logic 1, as shown in Fig. 2-10b, defines a negative logic system. The terms positive and negative are somewhat misleading since both signal values may be positive or both may be negative. It is not signal polarity that determines type of logic, but rather the assignment of logic values according to the relative amplitude of the signals. Integrated circuit data sheets define digital functions not in terms of logic 1 or logic 0, but rather in terms of H and L levels. It is up to the user to decide on a positive or negative logic assignment. The high-level and low-level voltages for the three IC digital logic families are listed in Table 2.7. In each family, there is a range of voltage values that the circuit will recognize as a high or low level. The typical value is the most commonly encountered. The table also lists the voltage supply requirements for each family as a reference. TTL has typical values of H 3.5 volts and L equals 0.2 volt. ECL has two negative values, with H equals minus 0.8 volt and L equals minus 1.8 volt. Note that even though both levels are negative, the higher one is minus 0.8. CMOS gates can use a supply voltage VDD anywhere from 3 to 15 volts. Typically, either 5 or 10 volts is used. The signal values in CMOS are a function of the supply voltage with H equals VDD and L equals 0 volt. The polarity assignments for positive and negative logic are also indicated in the table. In light of this discussion, it would be necessary to justify the logic symbols used for the ICs listed in Figure 2.9. Take, for example, one of the gates of the 7400 IC. This gate is shown in Block 58 Chapter 2 Table 2, 7H and L levels in IC logic families. IC family type voltage supply V, high level voltage, V, low level voltage, V, range, typical.
TTL ECL CMOS positive logic, negative logic.
TTL ECL CMOS positive logic, negative logic. VCC equals 5 VE equals minus 5.2 VDD equals 3 to 10 2.4 to 5, 0.95 minus 0.7 VDD, 3.5 minus 0.8 VDD logic, 1 logic. 0 minus 0.4 minus 1.9 to minus 1.60 to 0.5 0.2 minus 1.80 logic, 0 logic 1. Diagram form in Fig. 2-11b. The manufacturer's truth table for this gate given in a data sheet is shown in Fig. 2-11a. This specifies the physical behavior of the gate, with H being typically 3.5 volts and L being 0.2 volt. This physical gate can function as either a NAND or NOR gate, depending on the polarity assignment. Equals 1. The truth table of Fig. 2-11c assumes positive logic assignment with H and L equals 0. Checking this truth table with the truth tables in Figure 2.5, we recognize it as a NAND gate. The graphic symbol for a positive logic NAND gate is shown in Fig. 2-11d and is similar to the one adopted previously. L equals 1. Now consider the negative logic assignment for this physical gate with and H equals 0. The result is the truth table shown in Fig. 2-11e. This table can be recognized to represent the XYZ. HHHLYLHLHXLLHHTTL 7400 gate Z. A. Truth table in terms. B. Gate block diagram of H and LXYZ 0101111000011XYZ. C. Truth table for positive logic. H. D. Graphic symbol. Equals 1. L equals 0. NAND gate. XYZ 101000111100XYZ. E. Truth table for negative logic. F. Graphic symbol. L equals 1. H equals 0. NOR gate. Figure 2.11 demonstration of positive and negative logic. Boolean algebra and logic gates 59. NOR function, even though its entries are listed backwards. The graphic symbol for a negative logic NOR gate is shown in Fig. 2-11f. The small triangle in the input and output wires designates a polarity indicator. The presence of this polarity indicator along a terminal indicates that negative logic is assigned to the terminal. Thus, the same physical gate can function either as a positive logic NAND or as a negative logic NOR. The one drawn in the diagram is completely dependent on the polarity assignment that the designer wishes to employ. In a similar manner, it is possible to show that a positive logic NOR is the same physical gate as a negative logic NAND. The same relation holds between and OR gates or between exclusive OR and equivalence gates. In any case, if negative logic is assumed in any input or per terminal, it is necessary to include the polarity indicator triangle symbol along the terminal. Some digital designers use this convention to facilitate the design of digital circuits when NAND or NOR gates are used exclusively. We will not use this symbology in this book, but will resort to other methods for designing with NAND and NOR gates. Note that the ICs presented in Fig. 2-9 are shown with their positive logic graphic symbols. They could have been shown with their negative logic symbols if one wished to do so. The conversion from positive logic to negative logic, and vice versa, is essentially an operation that changes L's to zeros and zeros to ones in both inputs and output of a gate. Since this operation produces the dual of a function, the change of all terminals from one polarity to the other results in taking the dual of the function. The result of this conversion is that all AND operations are converted to OR operations, or graphic symbols, and vice versa. In addition, one must not forget to include the polarity indicator in graphic symbols when negative logic is assumed. The small triangle that represents a polarity indicator and the small circle that represents a complementation have similar effects, but different meanings. Therefore, one can be replaced by the other, but the interpretation is different. A circle followed by a triangle, as in Fig. 2-11f, represents a complementation followed by a negative logic polarity indicator. The two cancel each other, and both can be removed. But if both are removed, then the inputs and output of the gate will represent different polarities. 2.8.2 Special Characteristics. The characteristics of IC digital logic families are usually compared by analyzing the circuit of the basic gate in each family. The most important parameters that are evaluated and compared are fan-out, power dissipation, propagation delay, and noise margin. We first explain the properties of these parameters and then use them to compare the IC logic families. Fan-out specifies the number of standard loads that the output of a gate can drive without impairing its normal operation. A standard load is usually defined as the amount of current needed by an input of another gate in the same IC family. Sometimes the term loading is used instead of fan-out. This term is derived from the fact that the output of a gate can supply a limited amount of current, above which it ceases to operate properly, and is said to be overloaded. The output of a gate is usually connected to the inputs of other similar gates. Each input consumes a certain amount of power from the gate input, so that each additional connection adds to the load of the gate. Loading rules are usually listed for a family of standard digital circuits. These rules specify the maximum amount of loading allowed for each output of each circuit. Exceeding the specified maximum load may cause a malfunction because the circuit cannot supply the power demanded from it. The fan-out is the maximum number of inputs that can be connected to the output of a gate, and it is expressed by a number. 60 Chapter 2. The fan-out capabilities of a gate must be considered when simplifying Boolean functions. Care must be taken not to develop expressions that result in an overloaded gate. Non-inverting amplifiers or buffers are sometimes employed to provide additional driving capabilities for heavy loads. Power dissipation is the supplied power required to operate the gate. This parameter is expressed in milliwatts, MW, and represents the actual power dissipated in the gate. The number that represents this parameter does not include the power delivered from another gate. Rather, it represents the power delivered to the gate from the power supply. An IC with 4 gates will require, from its power supply, 4 times the power dissipated in each gate. In a given system, there may be many ICs, and the power required by each IC must be considered. The total power dissipation in a system is the sum total of the power dissipated in all ICs. Propagation delay is the average transition delay time for a signal to propagate from input to output when the binary signals change in value. The signals through a gate take a certain amount of time to propagate from the inputs to the output. This interval of time is defined as the propagation delay of the gate. Propagation delay is expressed in nanoseconds, ns, and 1 nanosecond is equal to 10⁻⁹ of a second. The signals that travel from the inputs of a digital circuit to its outputs pass through a series of gates. The sum of the propagation delays through the gates is the total propagation delay of the circuit. When speed of operation is important, each gate must have a small propagation delay, and the digital circuit must have a minimum number of series gates between inputs and outputs. The input signals in most digital circuits are applied simultaneously to more than one gate. All those gates that receive their inputs exclusively from external inputs constitute the first logic level of the circuit. Gates that receive at least one input from an output of a first logic level gate are considered to be in the second logic level, and similarly for third and higher levels. The total propagation delay of the circuit is equal to the propagation delay of a gate times the number of logic levels in the circuit. Thus, a reduction in the number of logic levels results in a reduction of signal delay and faster circuits. The reduction of the propagation delay in circuits may be more important than the reduction in the total number of gates if speed of operation is a major factor. Noise margin is the maximum noise voltage added to the input signal of a digital circuit that does not cause an undesirable change in the circuit output. There are 2 types of noise to be considered. DC noise is caused by a drift in the voltage levels of a signal. AC noise is a random pulse that may be created by other switching signals. Thus, noise is a term used to denote an undesirable signal that is superimposed upon the normal operating signal. The ability of circuits to operate reliably in a noise environment is important in many applications. Noise margin is expressed in volts, V, and represents the maximum noise signal that can be tolerated by the gate. 2.8.3 Characteristics of IC logic families. The basic circuit of the TTL logic family is the NAND gate. There are many versions of TTL, and 3 of them are listed in Table 2.8. This table gives the general characteristics of the IC logic families. Values listed are representative on a comparison basis. For any one family or version, the values may vary somewhat. The standard TTL gate was the first version of the TTL family. Additional improvements were added as the technology progressed. The Schottky TTL is a later improvement that reduces the propagation delay but results in an increase in power dissipation. The low-power Schottky TTL version sacrifices some speed for reduced power dissipation. It has the same propagation. Boolean algebra and logic gates. 61 Table 2.8 Typical characteristics of IC logic families. IC logic fan-out power dissipation propagation noise margin family, MW, delay, NS, V. Standard TTL 10-10-10-0.4 Schottky TTL 10-22-30.4 Low power Schottky TTL 22-10-0.4 ECL 25-25-20.2 CMOS 50.0.125.3 Delay as the standard TTL, but the power dissipation is reduced considerably. The fan-out of the standard TTL is 10, but the low-power Schottky version has a fan-out of 20. Under certain conditions, the other versions may also have a fan-out of 20. The noise margin is better than 0.4 V, with a typical value of 1 V. The basic circuit of the ECL family is the NOR gate. The special advantage of ECL gates is their low propagation delay. Some ECL versions may have a propagation delay as low as 0.5 nanoseconds. The power dissipation in ECL gates is comparatively high and the noise margin low. These two parameters impose a disadvantage when choosing ECL over other logic families. However, because of its low propagation delay, ECL offers the highest speed of any family and is thultimetechoice for very fast systems. The basic circuit of CMOS is the inverter from which both NAND and NOR gates can be constructed. The special advantage of CMOS is its extremely low power dissipation. Under static conditions, the CMOS gate power dissipation is negligible and averages about 10 nW. When the gate signal changes state, there is a dynamic power dissipation which is proportional to the frequency at which the circuit is exercised. The number listed in the table is a typical value of dynamic power dissipation in CMOS gates. The one major disadvantage of CMOS is its high propagation delay. This means that it is not practical for use in systems requiring high-speed operations. The characteristic parameters for the CMOS gate depend on the power supply voltage VDD that is used. The power dissipation increases with increase in voltage supply. The propagation delay decreases with increase in voltage supply, and the noise margin is estimated to be about 40% of the voltage supply value. References: 1. Boole, G. An Investigation of the Laws of Thought. New York, Dover Rub, 1954. 2. Shannon, C. E. A Symbolic Analysis of Relay and Switching Circuits. Trans of the AIE, Volume 57, 1938, 713-23. 3. Huntington, E.V. Sets of Independent Postulates for the Algebra of Logic. Trans. A.M. Math. SOC, Volume 5, 1904, 288-309. 4. Burkhoff, G. and T.C. Barty, Modern Applied Algebra, New York, McGraw-Hill Book Company, 1970. 5. Burkhoff, G. and S. McLean, A Survey of Modern Algebra, 3rd edition. New York, The Macmillan Company, 1965. 6. Hone, F. E. Applied Boolean Algebra, 2nd edition. New York, The Macmillan Company, 1966. 62 Chapter 27. Whitesett, J. E. Boolean Algebra and Its Applications. Reading, Massachusetts. Addison Wesley Pub Company, 1961. 8. The TTL Data Book for Design Engineers, Dallas, Texas. Texas Instruments Incorporated, 1976. 9. MECL Integrated Circuits Data Book. Phoenix, Arizona. Motorola Semiconductor Products Incorporated, 1972. 10. RCA Solid State Data Book Series. COS/MOS Digital Integrated Circuits. Somerville, N.J. RCA Solid State DIV, 1974. Problems. 2-1. Which of the 6 basic laws, closure, associative, commutative, identity, inverse, and distributive, are satisfied for the pair of binary operators listed below? Plus 000000121011111. 220122222201201201222. Show that the set of three elements 0, 1, 2, and the two binary operators plus and ch, as defined by the above table is not a Boolean algebra. State which of the Huntington postulates is not satisfied. 2-3. Demonstrate by means of truth tables the validity of the following theorems of Boolean algebra. A. The associative laws. B. De Morgan's theorems for three variables. C. The distributive law of plus over 2-4. Repeat problem 2-3 using Venn diagrams. 2-5. Simplify the following Boolean functions to a minimum number of literals. A. XY y XY. B. XY, X.
Simplify the following Boolean functions to a minimum number of literals. A. xy and xy. B. x and y, x and y. C. xyz and xy and xyz. D. zx and zxy. E. a and b, a plus b. F. y, wz and wz, plus xy 2-6. Reduce the following Boolean expressions to the required number of literals. A. ABC and ABC and ABC.
F, y, wz, plus xy 2-6. Reduce the following Boolean expressions to the required number of literals. A. ABC plus ABC plus ABC plus ABC plus ABC to 5 literals. B. BC plus AB plus BCD to 4 literals. C. CD plus A plus CD plus AB to 3 literals. D. A plus C plus D, A plus C plus D, A plus C plus D, A plus B to 4 literals 2-7. Find the complement of the following Boolean functions and reduce them to a minimum number of literals. A. BC plus AD, AB plus CD, B. BD plus ABC plus ACD plus ABC. C. AB, A, AB, B, D, AB, E. Boolean algebra and logic gates 63 2-8. Given two Boolean functions f1 and f2. A. Show that the Boolean function e equals f1 plus f2 obtained by ORing the two functions contains the sum of all the minterms in f1 and f2. B. Show that the Boolean function g equals f1 f2, obtained from ANDing the two functions, contains those minterms common to both and f1, f2. 2-9. Obtain the truth table of the function. F equals xy plus yz 2-10. Implement the simplified Boolean functions from problem 2-6 with logic gates. 2-11. Given the Boolean function, f equals xy plus yz. A. Implement it with and, or, and not gates. B. Implement it with only, or, and not gates. C. Implement it with only and not gates. 2-12. Simplify the functions t1 and t2 to a minimum number of literals. A. B C T 1 T 2 0 0 0 1 0 0 0 1 1 0 0 1 0 1 0 0 1 1 0 1 1 0 0 0 1 1 0 1 0 1 1 1 0 0 1 1 1 1 0 1 2-13. Express the following functions in a sum of minterms and a product of max terms. A F A B C D equals D, a plus B D B, F, W, X, Y, Z equals YZ plus WXY plus WXZ plus WXZ. Plus A equals A plus B, I plus C plus D, C, F, A, B, C, D plus B plus C, A, D, B plus C plus D equals A plus D, F, A, B, C, B, B plus C, E, F, X, Y, Z equals 1 F, X, Y, Z equals XY plus Z, Y plus XZ. 2-14. Convert the following to the other canonical form. A, F, X, Y, Z, Sigma. N3, Epta, B, F.
2-14. Convert the following to the other canonical form. A, F, X, Y, Z, equals sigma, 1.3, 7, B, F, A, B, C, D, equals sigma, 0, 2, 6, 11, 13, 14, C, F, X, Y, Z, equals pi, 0, 3, 6, 7, D, F, A, B, C, D, equals pi, 0, 1, 2, 3, 4, 6, 12. 64 Chapter 2 2 to 15 What is the difference between canonical form and standard form? Which form is preferable when implementing a Boolean function with gates? Which form is obtained when reading a function from a truth table? 2 to 16 The sum of all minterms of a Boolean function of n variables is 1. A. Prove the above statement for n equals 3. B. Suggest a procedure for a general proof. 2 to 17 The product of all maxterms of a Boolean function of n variables is 0. A. Prove the above statement for n equals 3. B. Suggest a procedure for a general proof. Can we use the duality principle after proving B. of problem 2 to 16? 2 to 18 Show that the dual of the exclusive OR is equal to its complement. 2 to 19 By substituting the Boolean function equivalent of the binary operations as defined in Table 2.6, show that A. The inhibition and implication operators are neither commutative nor associative. B. The exclusive OR and equivalence operators are commutative and associative. C. The NAND operator is not associative. D. The NOR and NAND operators are not distributive. 2 to 20 A majority gate is a digital circuit whose output is equal to 1 if the majority of the inputs are LS. The output is 0 otherwise. By means of a truth table, find the Boolean function implemented by a 3-input majority gate. Simplify the function. 2 to 21 Verify the truth table for the 3-input exclusive OR gate listed in Fig. 2-8, C. List all 8 combinations of x, y, and z, evaluate a equals xy, then evaluate f equals az equals xyz 2 to 22. TTL-SSI come mostly in 14-pin packages. 2 pins are reserved for power supply and the other pins are used for input and output terminals. How many gates are enclosed in one such package if it contains the following types of gates? A. 2-input exclusive OR gates. B. 3-input AND gates. C. 4-input NAND gates. D. 5-input NOR gates. E. 8-input NAND gates. 2 to 23 show that a positive logic AND gate is a negative logic OR gate, and vice versa. 2 to 24. An IC logic family has NAND gates with fan-out of 5 and buffer gates with fan-out of 10. Show how. The output signal of a single NAND gate can be applied to 50.
The output signal of a single NAND gate can be applied to 50 other gate inputs. 2 to 25. Implement YX-NOR gate using minimum number of NAND gate and NAND gates using minimum number of NOR gates. X, Y, Z, Z, 2 a 26. Show that
X, Y, Y, Z, Z, 2 to 26. Show that X equals 2 to 27. With examples, make out difference between A. Min term and max term, B. Positive and negative. Logic. 2 to 28 Differentiate between standard TTL, Schottky.
Logic. 2 to 28. Differentiate between standard TTL, Schottky TTL, ECL, and CMOS IC logic families in terms of fan-out, noise margin, propagation delay, and power dissipation.